Hello fellow sapiens, and welcome to Sleepless Homo. Before we dive in, take a moment to quiet yourself, calm your mind, and settle into this slow storytelling. Whether you're preparing to drift off, or simply keeping company while working, cooking, showering, or driving, this is a place for soft science told gently, not wild speculation. If you value thoughtful, long-form explorations of deep time, I invite you to like and subscribe. It helps this kind of humble, evidence-based science reach more people, and maybe add a little more curiosity to the world. I'd love to know how you use this channel. Do you fall asleep to it, or listen on headphones while you work? Or perhaps tell us where you're watching from. And if you happen to drift off during a chapter, don't worry. I've placed timestamps in the description so you can return tomorrow and pick up exactly where you left. The story is worth hearing from beginning to end. So with that, let's begin tonight's journey into the Triassic, a period when Earth rebuilt itself after the greatest extinction of all time. And as always, stay curious, stay calm. Tonight we begin with a moment in Earth's history that feels almost impossible to imagine. What happens when 90% of life vanishes and the planet has to start over? The calendar of the planet tells us that around 252 million years ago, at the end of the Permian, the biosphere suffered the worst crisis it has ever endured. We call it the Great Dying. To say that almost all living species disappeared is a statement so blunt that it almost loses meaning. But imagine a forest where 9 out of 10 trees fall, where almost every insect disappears, where reefs are stripped down to bare rock, where the great animals on land collapse one after another, until the silence is louder than the wind. That is the world that the Triassic inherited. It was not a gentle reset, it was a wound cut across every environment at once. The reveal begins when you notice the gaps. When paleontologists sift through the rocks laid down just after the Permian extinction, they find emptiness where there should be variety. Sediment beds that once held a riot of shells, sponges, corals and fish show only a few survivors. Entire groups that had dominated for hundreds of millions of years, like the rugose and tabulate corals, are simply gone. On land, the great forests collapsed into patchy wastelands. Rivers cut through barren valleys carrying sediment that no roots were holding down. Soil itself became a fragile memory. The fossil record after this event is marked by strange layers of microbial mats and disaster taxa, the opportunistic species that step in when everyone else is gone. So what happened to the Earth itself? The evidence points to a chain reaction driven by vast volcanic outpourings in Siberia. Today we call them the Siberian Traps. For hundreds of thousands of years, lava spilled across millions of square kilometers, releasing unimaginable quantities of carbon dioxide, sulfur dioxide, and methane. The planet suffocated under warming, acidification, and poisoned rain. Oxygen in the oceans collapsed to near zero. Anaerobic microbes which thrive without oxygen bloomed and produced toxic hydrogen sulfide that further choked marine life. It was not one killer but many, each making the others worse. For years after, the land remained unstable. Temperatures spiked to extremes, perhaps 50 degrees Celsius in some continental interiors. Such heat left the world's equatorial belt nearly uninhabitable for complex animals. Deserts stretched across much of Pangaea. Plants with seeds survived, but even they were sparse at first. Without dense vegetation, herbivores found little to eat. Without herbivores, carnivores had little to hunt. Ecological pyramids crumbled. Recovery had to start from the base, from the simplest survivors. One of the most striking consequences was what scientists call the coal gap. For roughly 10 million years after the extinction, there is almost no evidence of coal formation. Normally, lush wetland forests die, compress and form coal seams, but during this time the forest simply did not exist. Imagine a world where the vast swampy ecosystems that had fueled both life and, in our modern age, our own industries, had simply vanished. The absence of coal is not just geological trivia, it is a signal of a planet stripped of its forests. Marine ecosystems faced their own version of the gap. Before the Great Dying, reefs built by corals and sponges anchored marine diversity. Afterward, reefs disappeared almost entirely. This reef gap lasted for over 10 million years. Without reefs, fish and invertebrates lost their homes. Shorelines that had been full of life became relatively empty seascapes. The whole architectural layer of the oceans was gone, and yet, in that silence, the seeds of something new were waiting. Microbial mats and stromatolites, which had been common in the earlier seas billions of years before, suddenly flourished again. With competitors gone, these ancient builders of the biosphere resurfaced. To walk along a shoreline then would have been to see environments that looked more like the Proterozoic than like the Carboniferous. Time itself seemed to loop back. The human instinct is to look for inevitability, to imagine that the dinosaurs were destined to rise from this devastation. But the fossil record does not give us inevitability. It gives us fragments. It shows us only that life clawed its way back in ways that seem at once desperate and inventive. The Triassic did not begin with dominance, it began with survival. The few lineages that held on, small therapsids, hardy reptiles, seed ferns and scattered mollusks, were less victors than they were refugees. One mystery is how such fragile survivors managed to persist through the chaos. Some geologists suggest that high-latitude regions may have served as refugia. Cooler climates near the poles might have provided a sanctuary from the searing heat of the equator. Fossils from what is now South Africa and Russia support this idea. If so, then the ancestors of many later lineages may have clung to life in these marginal zones, waiting for conditions to ease. Even so, the recovery was uneven. Some groups began to diversify relatively quickly. Insects, for example, show signs of bouncing back within a few million years, but larger vertebrates struggled. Ecosystems that once supported a wide range of predators and herbivores collapsed into simpler food webs dominated by a handful of species. It would take tens of millions of years before anything like ecological complexity returned. From a scientific perspective, what makes this moment fascinating is not just the devastation, but the way it rewrote the rules. Traits that had once been advantageous were suddenly liabilities. Large body size, for example, had been a hallmark of late Permian ecosystems, with massive herbivores and predators roaming the continents. After the extinction, such giants were almost entirely gone. Smaller, more generalist species had the advantage. Speed of reproduction and flexibility of diet mattered more than strength or size. The haunting question is how close life came to collapsing completely. If 90% of species were extinguished, could it have gone further? Was there a threshold at which complex life might never have recovered? The rock record cannot tell us. It shows only that enough diversity survived to seed the next wave of evolution. But the idea lingers that the Triassic might easily never have happened at all. The image that emerges is one of a wounded planet. Rivers carried red sediments into shallow seas. Land baked under unrelenting sun. Forests were stunted, sparse, or absent. Ocean waters were often stagnant and toxic. Life did not march confidently into the Triassic. It limped, and yet in that limping came the chance for something new. This is why paleontologists describe the Triassic as a time of experimentation. With so much gone, the survivors had room to try again. Ecological roles were empty, niches were waiting. But at this opening stage, what we see most clearly is the cost of the great dying. The Triassic story begins not with dinosaurs or pterosaurs or ichthyosaurs, but with absence. To understand the strange abundance that would come later, we must first sit with the silence that came before. As humble observers, we must also admit that we cannot reconstruct every detail. The triggers of the extinction are still debated. The timing of recovery varies between regions and groups. Each fossil bed gives us a glimpse, but never the full picture. Scientists do their best with the evidence at hand, but there are gaps we may never fill. What we can say with confidence is that the Triassic was born in catastrophe, and that its first millions of years were shaped by survival in a world stripped bare. And so the haunting question remains, if Earth had to start over from near nothing 252 million years ago, how many times has chance, rather than inevitability, guided the path of life? And how fragile, then, is the balance we live within today? What was it like to stand on Pangaea, one continent stretching almost from pole to pole? To imagine it properly, you have to forget the familiar outlines of our world. There were no scattered continents, no Atlantic Ocean, no distinct North and South America. Instead, there was one vast landmass, a single supercontinent, its coastlines rimmed by a single global ocean that geologists call Panthalassa. To the east lay a smaller sea, the Tethys, a warm expanse that would one day close and open again in the making of the Mediterranean. But in the early Triassic, between 252 and 247 million years ago, it was Pangaea that dominated, and it shaped life as much as climate or extinction had. The reveal begins with geography. Imagine walking inland from any shoreline. For hundreds, sometimes thousands of kilometres, there would be no relief, no ocean breeze, only arid interiors. Supercontinents create deserts by their very nature. Moisture from the sea cannot penetrate far into the continental heart, so rain shadows stretch across enormous distances. Much of Pangaea's interior was likely barren, with seasonal extremes of heat and cold. Fossil soils from this time show little organic material, supporting the idea that great stretches of land were sparsely vegetated. This was not a world of lush, continuous forests, but one where pockets of life clung along coasts, rivers and lowland basins, while much of the centre remained dry and exposed. At high latitudes, conditions were somewhat different. Here the long winters and lower sun provided cooler climates, and some paleobotanical evidence suggests that hardy conifers and seed ferns grew in these regions. These belts may have served as refuges when equatorial zones overheated, providing habitat for the ancestors of later lineages. But for the majority of species, the low-latitude interiors were punishing. Climate models and isotopic data suggest average temperatures in many equatorial areas soared well above 40 degrees Celsius, sometimes higher, making them inhospitable for many complex animals. The land itself recorded these patterns. Red beds, sedimentary layers stained by iron oxides, are widespread in early Triassic deposits. They tell us of oxidizing conditions in arid environments, of ephemeral rivers and flash floods carving channels that quickly dried to cracked mud. These were landscapes of scarcity, where survival depended on endurance. Life at the margins, quite literally, was the rule. Coastal plains, monsoon belts and flood basins offered more reliable water and vegetation. These marginal zones became the laboratories of recovery, where plants re-established and vertebrates returned. One of the striking features of Pangaea was the strength of its monsoons. A supercontinent heats unevenly. Vast interiors bake under the sun, while ocean air masses remain cooler. The contrast drives powerful seasonal winds. Evidence from ancient river deposits and plant fossils suggests alternating wet and dry seasons in monsoon belts, particularly near the Tethys margins. For organisms that could endure, these rhythms offered opportunity. Seasonal floods replenished soils and filled wetlands, allowing temporary abundance before the return of drought. But they also demanded resilience, for in a few months the landscape could shift from floodplain to desert. For animals, this geography dictated possibility. Species that could travel long distances, tolerate drought, or exploit seasonal resources stood the best chance. Smaller-bodied creatures, with shorter reproductive cycles, could adapt quickly to these oscillations. Larger-bodied herbivores and predators, which had flourished in the lush Permian, were mostly gone, their energy needs too great for such unstable ecosystems. It is no coincidence that many of the first radiating lineages of reptiles and synapsids in the Triassic show adaptations to arid conditions, burrowing, water conservation, heat tolerance. Even plant life bore the imprint of Pangaea's vastness. Seed-bearing plants, with their protective coats and independence from constant water for reproduction, had the advantage. Their spores or seeds could wait through drought until the rains returned. Conifers, cycads and ginkgo phytes began to spread in these conditions, exploiting the drier interiors where ferns and leucopsids struggled. Their success laid the groundwork for the forests that would eventually spread across Triassic landscapes. Standing on this continent, had we been there, we would have seen horizons unbroken by mountain ranges for weeks of travel. Winds would whip across flat plains. Dust storms might have been common, lifting fine sediments from barren ground. Rivers would appear in the wet season, only to vanish into braided channels and dry beds. It was a world where permanence was rare, and adaptability was everything. The haunting question is whether life could truly thrive under such conditions, or whether it merely endured, waiting for relief. The fossil record suggests both. Recovery was real. Plants returned, insects diversified, reptiles began to radiate. But it was a recovery constrained by the geography of one giant continent under heat. Until Pangaea began to crack and humidity increased, the biosphere lived at the mercy of deserts and monsoons. For millions of years, survival itself was the greatest achievement. And yet, even in this severe landscape, there were gradients and subtleties. Pangaea was not uniformly dry. Along its coasts, especially those bordering the Tethys Ocean, conditions were more forgiving. These were zones where humidity built, where rivers could form consistent deltas, and where vegetation managed to recover more quickly than in the central deserts. Fossil pollen and plant impressions from these coastal basins show a greater diversity than inland deposits, including conifers and seed ferns that hint at more stable habitats. For early reptiles and synapsids clinging to survival, these margins were lifelines. They could graze, hunt, and reproduce with more security than in the vast arid heart of the continent. One way scientists trace these ancient climate belts is through the study of paleosols, ancient soils preserved in the rock record. Their mineral compositions, root traces, and chemical signatures tell of how much rainfall once soaked the ground, and whether vegetation could take hold. In the early Triassic, many of these paleosols are poorly developed, thin, and low in organic matter, confirming that conditions were harsh and vegetation sparse. But along the coasts, soils are richer, suggesting forests and more enduring ecosystems. These differences remind us that even a world dominated by desert still contained pockets of green resilience. Monsoon systems along the margins of Pangaea would have been dramatic. Seasonal contrasts in rainfall may have been greater than anything we experience today. In the wet months, rivers flooded their banks, spreading nutrient-rich silt across wide plains. In the dry season, those same plains cracked into parched earth. Fossilized mud cracks, evaporate deposits like gypsum and halite, and alternating sediment layers all preserve these cycles. For organisms adapted to take advantage of boom and bust environments, these patterns could be opportunities. Fast-growing plants germinated quickly with seasonal rains. Small herbivores fed and reproduced before the return of drought. Predators followed, exploiting the brief pulse of abundance. Geologists have also modelled how Pangaea's shape influenced global wind patterns. With so much landmass, heat built up in the continental interior far more than over the surrounding seas. This thermal contrast likely drove intense atmospheric circulation, shifting storm tracks and concentrating rainfall along the coasts while leaving the interior scorched. The circulation would have amplified both aridity and seasonality, setting the stage for evolutionary pressures unlike those of smaller, more fragmented continents. If we ask what it felt like to stand on this supercontinent under heat, the answer is not simple. It would depend on where you stood. At the margins, you might hear the sound of monsoon rains, rivers swollen with life, plants bursting into brief abundance. Far inland, you might stand in silence broken only by wind and dust, under skies hazy with heat, where survival was measured in endurance rather than abundance. This was the paradox of Pangaea, a single landmass that held both promise and desolation, shaping the paths of evolution by its very scale. Why did plants with seeds survive, while so many others vanished? That question lingers at the heart of the early Triassic, because when the dust of the Great Dying settled, the first signs of resilience were green. Where once the lush forests of the Permian had spread in dense swathes, only fragments remained, and yet among those fragments, the plants that carried their future within a hardened case stood the best chance. To walk through the early Triassic landscape, if we could, would have been to see scattered groves rather than continuous canopies, isolated clusters of seed ferns or hardy conifers rising from otherwise barren expanses. These survivors owed their persistence to the evolutionary innovation of the seed, a capsule of life that could endure drought, heat, and scarcity until conditions turned. The reveal begins with the contrast. Before the extinction, many dominant plant groups reproduced by spores. Spore-bearing plants such as lycopsids and many ferns depended on water for reproduction, Their tiny gametes needed a film of moisture to move, which made them vulnerable in a world stripped of wetlands and dominated by arid climates. When rainfall became erratic and drought spread across Pangaea, these plants faltered. Seed plants, by contrast, did not need open water to reproduce. Their pollen could be carried by wind. Their seeds enclosed an embryo in protective tissue with a supply of stored nutrients. This meant that even when rains were absent, even when soil cracked and rivers vanished, the potential for life could wait inside those resilient shells. One of the earliest and most conspicuous groups to survive were the seed ferns, or pteridosperms. They looked like ferns, with large fronds, but unlike true ferns, they bore seeds. In the early Triassic, genera like Glossopteris had already declined, particularly in Gondwana where they had dominated Permian landscapes, but other seed ferns held on. Their fossilized leaves appear scattered through Triassic deposits, suggesting that even in an unstable climate they could colonize disturbed soils and spread into openings where forests had fallen. Seed ferns often grew as pioneering plants, tolerating harsher conditions and creating footholds that allowed other vegetation to follow. Alongside them, conifers began to expand. These ancestors of today's pines, spruces and cedars were already present in the Permian, but the Triassic opened new opportunities. Conifers were well suited to dryness. Their needle-like leaves reduced water loss, and their seeds could wait through long intervals before germinating. By the Middle Triassic, conifers began to appear in more extensive forests, but even in the earlier stages their fossils are found along the margins of rivers and coastal belts where moisture was more reliable. Their tall trunks and dense canopies created microhabitats, offering shade and stabilizing soils. In a landscape stripped of complexity, conifers began to restore vertical structure to ecosystems. These early seed plants were not alone. Other gymnosperms, such as cycades and ginkgo relatives, also made appearances. Cycades, with their stout trunks and crown of tough leaves, were especially resilient to poor soils and erratic rainfall. They may have grown in scattered groves across semi-arid regions, their large seeds dispersed by gravity, or carried short distances by animals. Ginkgophytes, which today survive in only a single species, had a wider distribution in the Triassic. Their fan-shaped leaves appear in fossil beds, hinting at a once diverse group that thrived in the recovering forests. The information preserved in these fossils is often subtle. Paleobotanists piece together climate and ecology from the size and shape of leaves, the cuticle structures on their surfaces, the pollen grains that drifted into sediments and were preserved. In early Triassic deposits, the pollen record shows a marked dominance of gymnosperm pollen. This is direct evidence that seed plants, more than any other group, were filling the ecological vacuum. The presence of these pollen grains in far-flung regions, from what is now Europe to Asia to Gondwana, indicates that gymnosperms had not only survived but were spreading. Forests regrowing after the extinction did more than provide shade and food. They stabilized soils, reducing erosion from seasonal floods. They fix carbon, influencing the atmosphere in a planet struggling with elevated greenhouse gases. They offered shelter and microclimates, places where humidity lingered and temperature extremes were buffered. In this way, seed plants were not just survivors but engineers of recovery. Without their persistence, vertebrate life on land would have faced even greater obstacles. And yet, the forests of the early Triassic were not the forests we know today. They were patchy, uneven and vulnerable. Vast tracts of land remained barren. Where trees stood, they often did so in isolation, like islands of stability in seas of desert. Recovery was slow, measured not in centuries but in millions of years. Each step forward could be erased by drought, fire, or flood. What makes the story humbling is how close it seems to balance between collapse and renewal. In thinking about why seeds mattered so much, it is useful to imagine time stretched thin. A seed does not guarantee survival, it is a wager. Inside its protective coat is the gamble that conditions will turn before its stored energy is spent. In the Triassic, this wager was repeated billions of times, scattered across dust and floodplain. Enough of those wagers succeeded that forests began to return. This strategy, betting on the future, proved decisive in a world that had lost its stability. Resolution comes in the haunting question: if not for the resilience of seeds, would terrestrial ecosystems ever have rebuilt themselves? The Triassic shows us that plants, silent and often overlooked in these stories, were the true architects of recovery. Without them, animals would have had no foundation. Every reptile, every mammal ancestor, every insect that returned owed its survival to patches of forest that endured because seeds could wait. And so we are reminded that even in times when life seemed broken beyond repair, a small capsule of potential could hold the key to the next age. As the supercontinent baked under its uneven skies, the very shape of Pangaea had dictated where life could cling on. But once the floods receded and the dust settled, it was not animals that led the first real wave of recovery. It was the plants. Wherever the soil could hold even a little moisture, the green world began to push back against emptiness. The lesson of the early Triassic is that the groundwork of all future diversity was laid by vegetation. Without roots, shade, and leaf litter, there would have been no habitats to shelter vertebrates or invertebrates, no food webs sturdy enough to support carnivores, no landscapes stable enough to endure floods or storms. The survivors that managed this feat were not the delicate spore bearers of the earlier Paleozoic, but a new cohort that had a secret weapon: seeds. Seeds offered a pause button in a world of chaos. Instead of relying on constant water to complete their life cycle, seed plants could bide their time. They could ride out years of drought sealed within a tough coat, carrying food reserves for the embryo inside. When rains returned, even briefly, they were ready to germinate. This strategy allowed them to occupy marginal lands, where older spore-producing plants could not persist. It is no coincidence that in the fossil record after the Great Dying, pollen grains from gymnosperms become abundant almost everywhere. The very dust of the Triassic tells us that seeds had tipped the balance, and so the rebirth of forests began in fits and starts. Conifers with their narrow leaves, cycads with their stout trunks, ginkgophytes with their fan-shaped foliage, and the seed ferns with their hybrid forms all stepped into the gaps left by extinction. They did not form continuous blankets of greenery as their Permian predecessors had, but rather scattered oases, green enclaves among vast red deserts. In these scattered patches life found footholds. Small reptiles could shelter beneath the branches, rivers stabilized under the grip of roots, the atmosphere itself shifted as plants drew down carbon dioxide. The stage was being reset for new experiments in animal evolution. When we picture the Triassic, it is easy to imagine only the flamboyant reptiles that would follow, or the return of predators to the seas. But none of those stories would exist without the quiet persistence of seeds. It was this evolutionary innovation that let plants endure heat, drought, and instability long enough to rebuild. And so, in order to understand the strange forest that began to emerge after catastrophe, we have to ask, why did plants with seeds survive, while so many others vanished? That is where the next step of our story begins. What happens to an ocean when reefs vanish for 10 million years? It is one of the most haunting questions the early Triassic leaves us with, because reefs are not merely pretty structures beneath the waves. They are the scaffolding of marine life, the three-dimensional architecture upon which entire ecosystems rest. To lose them is not simply to lose corals, it is to flatten the oceans, to erase the habitats that host countless species, and to strip the seas of their most complex communities. After the Great Dying 252 million years ago, that is precisely what happened. For millions of years afterward, paleontologists find no true reefs, only barren seabeds or microbial mats where once vast structures had thrived. This interval is known simply as the coral gap. The reveal comes when we remember what reefs had been. In the Paleozoic, especially in the Devonian and Carboniferous, reefs had been dominated by rugose and tabulate corals. Rugose corals, often horn-shaped in their solitary forms, and tabulate corals which built colonies of stacked chambers, had constructed reefs that teemed with life. Alongside sponges and algae, they had created intricate frameworks that supported fish, crustaceans, mollusks, and more. But these groups did not survive the end Permian extinction. The fossil record shows their disappearance with brutal clarity. By the earliest Triassic they were gone. Without them, the oceans were left without their primary builders. The reef gap stretches for about 10 to 14 million years, depending on region and dating method. In that interval, we see instead the proliferation of microbialites, carbonate structures made by microbial mats. These organisms, mostly cyanobacteria, had been dominant in Earth's early history billions of years before. In the absence of corals, they resurged, spreading across shallow seas and forming low, mound-like build-ups. They were primitive stand-ins for reefs, lacking the vertical complexity and diverse niches of coral frameworks. For marine life, this meant a severe contraction of habitats. Fish and invertebrates had fewer places to hide, feed, or reproduce. It is not an exaggeration to say that the loss of reefs rewrote ocean ecology for an entire epoch. The information scientists use to reconstruct this gap comes from carbonate platforms preserved on multiple continents. In early Triassic strata, instead of corals or sponges, they find thick accumulations of stromatolites and thrombolites, layered or clotted microbial carbonates. These deposits often form directly after mass extinctions, suggesting that microbes step in when ecosystems collapse, filling roles until more complex organisms return. In the Triassic, their reign was unusually long. That duration tells us how slow the recovery of marine ecosystems truly was. Eventually, though, the seas did change. By the Middle Triassic, a new kind of coral appears in the record, the scleractinians. These are the ancestors of the corals we know today. Their skeletons are made of aragonite rather than calcite, and their colony structures differ from those of the Paleozoic forms. Their sudden emergence has puzzled paleontologists for decades. Did they evolve from surviving rugose ancestors that somehow escaped detection? Did they arise from anemone-like creatures that independently evolved hard skeletons? The truth is still uncertain. The coral gap has left us with too few clues. What we can say is that scleractinians rapidly diversified once they appeared, spreading across the Tethys Ocean and beyond, and within a few million years, reefs returned to the fossil record. The haunting question is what this disappearance and return meant for evolution. For 10 million years, countless lineages had to live without reef habitats. Did this delay diversification of marine groups that would otherwise have flourished earlier? Did it redirect the pathways of evolution entirely? It is difficult to know. We can only observe that when reefs finally did come back, the ocean seemed to exhale, filling with new diversity. The silence of the coral gap reminds us that ecosystems are not guaranteed to return quickly. They can vanish for spans of time longer than the entire history of humanity, and then reappear in different forms. And so we look back to those 10 million years of flattened seas and imagine the quiet. Shallow waters, once noisy with fish and invertebrates, became places of microbial carpets and scattered survivors. The Triassic Ocean, in its opening chapters, was not the vibrant stage we often picture, but a stripped world waiting for builders to return. When they finally did, in the form of scleractinians, the planet's long recovery could at last take a new step. The absence of reefs also reshaped the chemistry of the oceans themselves. In healthy reef systems, corals and calcareous algae act as major sinks for carbonates, locking minerals into their skeletons and balancing the chemistry of seawater. Without those builders, the balance shifted. The early Triassic seas often show evidence of supersaturation with calcium carbonate, yet little of it was being drawn into large reef structures. Instead, it precipitated as simpler deposits or became incorporated into microbial mats. This difference meant that ocean chemistry, normally buffered by reefs, swung more widely in response to volcanic outgassing and climate stress. Sediment layers from this interval tell us that shorelines were dominated by shifting sands and mudflats, rather than stable reef-bound lagoons. The sedimentological record shows greater evidence of erosion and reworking, suggesting that coasts were less protected from waves and storms. Reefs act as natural barriers. Without them, energy from storms travelled farther inland, rearranging sediments and further disturbing fragile habitats. It is easy to imagine that for millions of years the shallows were far more turbulent places, constantly in flux, and far less inviting for permanent colonization by complex communities. Yet even in this barren phase, hints of future change can be found. In certain localities, small patch reefs of sponges and algae appear intermittently, like isolated experiments that never quite took hold. These fragile build-ups remind us that the drive to reclaim space in the oceans never disappeared, only faltered under the weight of instability. When conditions finally improved, perhaps when greenhouse gases lessened and ocean oxygen levels rebounded, those experiments provided stepping stones for the rise of the scleractinians. When the first true scleractinian corals appear in the Middle Triassic, they do not trickle into the record slowly. Instead, they burst forth with a diversity that suggests hidden preparation. How did 4-foot skull amphibians dominate after nearly everyone else disappeared? It is one of the paradoxes of the early Triassic, because when so much of the animal kingdom had collapsed, the creatures that stepped forward to fill the empty landscapes were not sleek reptiles or nimble mammal ancestors, but lumbering survivors of an older world. The temnospondyls, a lineage of amphibians that had been present since the Carboniferous, suddenly rose to prominence. Their fossils appear in rivers, lakes and floodplains across what is now Europe, Asia and Gondwana. They had not only survived the Great Dying but flourished in its aftermath, diversifying into giant predators that could stretch to several meters in length. Among them were skulls so large that they alone measured 4 feet from snout to jaw hinge, a grotesque proportion that reminds us of how strange the Triassic really was. The reveal is that this dominance was both impressive and temporary. Temnospondyls like Mastodonsaurus and Plagiosaurus ruled niches left vacant by the collapse of reptiles and synapsids, but their power came with limits. They remained amphibians, tied to water for much of their lives, with skin that demanded moist environments and eggs that could not withstand prolonged drought. In a supercontinent dominated by aridity and seasonality, their flourishing was always precarious. Mastodonsaurus was one of the giants, known from Middle Triassic deposits in Europe. Its skull alone could be longer than most adult humans are tall. The head was broad and flat, studded with conical teeth and paired tusks on the lower jaw that projected upward into sockets in the skull roof. This anatomy suggests a predator that lurked in lakes or slow rivers, ambushing prey with sudden strikes. Its body, reconstructed from partial skeletons, stretched to 6 meters in length. For tens of millions of years after the extinction, Mastodonsaurus was one of the largest predators on land and in fresh water. It thrived where few others could, proof that gigantism was not reserved only for reptiles. Plagiosaurus, by contrast, shows how diverse temnospondyls could become. Its skull was wider than it was long, almost pancake-like, giving it a bizarre flat-headed appearance. The eyes were set high, suggesting a lifestyle of lying against the riverbed or a lake floor, watching the waters above. Its mouth, broad and filled with fine teeth, hints at suction feeding, perhaps drawing in fish or invertebrates with sudden gulps. The body was flattened as well, making Plagiosaurus look like an amphibian designed more by accident than intention, yet it clearly thrived in its environment. Fossil beds yield numerous specimens, indicating that it was a successful form during the Triassic. The information we have about temnospondyls comes not just from their bones, but from the sediments that surround them. Many fossils are found in fluvial deposits, ancient river systems, where seasonal floods alternated with drought. The abundance of temnospondyl remains in such settings suggests that these animals were both dominant and vulnerable. When water was abundant, they flourished. When rivers dried, mass death events may have claimed entire populations. Their dominance was thus cyclical, bound to the rhythms of Pangaea's unstable climate. Why did temnospondyls succeed when so many other groups collapsed? Part of the answer lies in their history. Temnospondyls were ancient generalists. They had survived previous upheavals and already possessed a wide range of body plans. Some resembled crocodiles, others salamanders, others flat-bodied specialists like Plagiosaurus. This flexibility meant that when ecosystems collapsed, at least some forms were already suited to the harsh new conditions. Their reproductive strategy also helped. Amphibians can produce large numbers of offspring quickly, and though many perish, the strategy ensures survival in unstable environments. In the Triassic, this capacity for rapid replacement may have been crucial, yet there were limits. Temnospondyls were never free from their amphibian constraints. Unlike reptiles, their eggs lacked protective shells. Their skin could desiccate under arid skies. They could never fully colonize the dry interiors of Pangaea. Instead, they remained tethered to rivers, lakes, and deltas, which restricted their expansion compared to reptiles that could spread across deserts and uplands. As the Triassic progressed and reptiles diversified, temnospondyls gradually ceded ground. By the end of the period, they were already in decline, relics of a time when amphibians briefly reclaimed the mantle of dominance. The haunting question is what their story tells us about survival. Were temnospondyls truly adapted to the Triassic world, or did they simply exploit a temporary gap before more versatile groups arrived? Their fossils suggest both. They were apex predators, shaping ecosystems for tens of millions of years, but their eventual decline shows that dominance after catastrophe can be fleeting. In the early Triassic, amphibians rose as giants with skulls the size of doors, but their reign was borrowed time. Their story also reminds us that recovery after extinction is rarely a straight climb upward. In many ways, temnospondyls represent what paleontologists sometimes call a disaster lineage, a group that rises to prominence not because it suddenly outcompetes rivals, but because rivals are gone. Their dominance in the early Triassic should not be mistaken for inevitability. It was circumstantial, made possible by absence. In a sense, they were caretakers of ecosystems that had lost their usual rulers, bridging the gap until more permanent players could take the stage. This role does not lessen their importance. Without them, many food webs would have been even thinner. But it does frame their success as a product of timing as much as adaptation. The evidence also shows that these amphibians left deep marks on their environments. Trackways preserved in ancient mudstones reveal heavy-bodied creatures dragging themselves between pools during dry spells, leaving furrows across cracked sediments. Bone beds suggest mass deaths during droughts. With dozens of individuals preserved together, their lives cut short when waters receded too quickly. Such findings paint a vivid picture of boom and bust existence, abundance during wet seasons, collapse during dry ones. This rhythm would have been familiar across much of Pangaea, where monsoon systems dictated survival. Even their anatomy hints at compromise. The immense skulls of Mastodonsaurus and its kin gave them power as ambush predators, but they also made locomotion awkward. Reconstructions suggest these amphibians were not agile hunters on land, but largely confined to aquatic ambush. Their teeth and jaw mechanics point to diets of fish and smaller tetrapods, yet their size made them vulnerable to water shortages. They were masters of their niche, but prisoners of its instability. And still, there is something remarkable in how long they persisted. For tens of millions of years after the extinction, temnospondyls remained among the largest vertebrates in freshwater ecosystems. Some lineages even continued beyond the Triassic into the Jurassic, long after their heyday had passed. Their persistence shows that even borrowed time can stretch across spans that dwarf human history. In the end, their legacy is both grand and fragile. They remind us that survival after crisis does not always mean progress toward modernity. Sometimes it means old lineages rising again, holding ecosystems together, and then fading when the world moves on. When we look back at the early Triassic and see amphibians with skulls the length of a dining table, we are not just looking at evolutionary curiosities. We are witnessing a moment when life, battered and reduced, leaned on its survivors, however unlikely, for stability. Their reign was temporary, but without them, the recovery of ecosystems might have been delayed far longer. When did fur and whiskers first brush against the world? The Triassic does not give us a perfect answer, only tantalizing hints. Among the reptiles that were experimenting with sails, horns and elongated necks, another lineage was quietly refining traits that would someday make them our ancestors. These were the cynodonts, a branch of synapsids that emerged from the wreckage of the Permian extinction and began to carry the mammalian blueprint forward. Their bones, scattered in Triassic sediments, reveal a suite of changes that look remarkably familiar to us. Upright limbs, differentiated teeth, and possible traces of whisker pits suggest that in their small, resilient bodies, some of the first fur-bearing animals may already have been padding through the dust. The reveal comes when we compare their skeletons to those of their Permian relatives. Earlier synapsids often sprawled like lizards, with limbs splayed to the side. Cynodonts, by contrast, show more upright postures, with the legs tucked beneath the body. This posture is not a trivial detail. It changes how an animal moves, how it breathes, and how efficiently it can sustain activity. Upright posture supports a more active lifestyle, freeing forelimbs for new functions and allowing lungs to ventilate more effectively. These changes hint at higher metabolic rates, a step closer to the warm-blooded physiology of mammals. In the fossil record, one of the most discussed features of cynodont skulls is the presence of small openings, or foramina, around the snout. Some paleontologists interpret these as evidence for vibrissae, the tactile hairs we know as whiskers. In living mammals, whiskers connect to nerves that carry information about touch and vibration, allowing animals to navigate in darkness or tight spaces. If cynodonts had them, it suggests that hair follicles had already evolved since whiskers are specialized hairs. And if hair follicles were present, then fur may not have been far behind. This line of reasoning, while indirect, is one of the strongest clues that hair originated in the Triassic or perhaps even earlier. Among the diverse cynodonts, Diademodon stands out as a frequent subject of study. Its fossils are found in South Africa, dating to the early and middle Triassic. At roughly the size of a medium dog, with robust skulls and powerful jaws, Diademodon shows both carnivorous and herbivorous adaptations. Its teeth include sharp canines, but also broad cheek teeth for grinding, a combination suggesting an omnivorous or flexible diet. This versatility may have been one of the reasons cynodonts survived when so many other lineages did not. Diademodon's skeletal structure also points toward more advanced features, including a secondary palate that allowed it to breathe while chewing, a trait we take for granted in mammals today. The information we piece together about cynodont biology is cautious. No fur has been directly preserved in their fossils. Instead, we infer from skeletal clues, comparative anatomy, and the evolutionary logic that fur had to have originated before the split of modern mammal lineages. Monotremes, marsupials, and placentals all have fur, and their last common ancestor lived deep in the Triassic. It seems unlikely that hair evolved more than once. Thus, somewhere among cynodonts, perhaps among forms like Diademodon, the world first felt the brush of fur against air. The resolution lies in how these creatures straddled two worlds. On one hand, they were still ancient synapsids, sharing the earth with amphibians and early reptiles, vulnerable to the same climatic instability as everyone else. On the other, they carried features that would define mammals for the rest of time: upright postures, more complex teeth, possible whiskers, and maybe fur. These were the quiet revolutions happening while more flamboyant Triassic animals stole the spotlight. The haunting question is not whether fur first appeared in this age, but whether we can ever know for certain. Fossilization is biased against soft tissues. We may never find a direct imprint of hair from the early Triassic. Yet in the dust of Pangaea, amid rivers and floodplains, creatures were already evolving the warmth and sensitivity that would later define our own lineage. If we pause for a moment and imagine the Triassic landscape from the perspective of a cynodont, the contrasts become clear. These animals were not the towering amphibians with skulls like furniture, nor the flamboyant reptiles experimenting with sails and horns. Instead, they were closer to the ground, quick in their movements, and attuned to subtler cues. Their size and posture hint at lives lived in the margins, scurrying between patches of shade, burrowing into soil for refuge, or waiting at the edges of rivers for smaller prey. In these roles, whiskers would have been invaluable. A sensitive snout could detect vibrations in the dark, feel the edges of tunnels, and give early warnings of predators. To possess such a tool would have been a quiet but decisive advantage in a world where survival depended on reacting to change. The development of a secondary palate, evident in Diademodon and other cynodonts, also underscores this shift toward mammal-like function. It meant that air could pass beneath the roof of the mouth, even as food was being processed. This ability allowed longer chewing and more efficient digestion, without the interruption of breath. Combined with differentiated teeth, incisors, canines, and molar-like cheek teeth, it points toward higher energy demands, consistent with at least partial endothermy. In a volatile Triassic climate of heat, drought, and seasonal extremes, the capacity to regulate internal temperature and sustain activity would have offered resilience. There is also evidence that some cynodonts experimented with burrowing lifestyles. Fossilized burrow systems in South Africa have been attributed to small Triassic cynodonts such as Thrinaxodon. Their skeletons were found curled within the tunnels, preserved by sudden floods or ash. The narrow shape of their ribs and the strong claws of their forelimbs support the interpretation of digging behaviour. Burrows would have provided stable microclimates, shelter from predators, and a safe environment for raising young. Here again, The possibility of fur and whiskers seems natural. A coat would insulate in cooler nights or underground chambers, while whiskers would aid in navigating tight tunnels. The evolutionary experimentation of cynodonts was broad. Some grew to the size of wolves, others remained small and rodent-like. Some specialized in meat, others in plants, still others in mixed diets. What united them was a trajectory toward mammalian characteristics. Each fossil provides another piece of the puzzle. The shape of jaw bones transitioning toward the tiny ear ossicles of mammals, the arrangement of limb girdles shifting toward more efficient strides, the increasing complexity of teeth marking the move toward precise food processing. These were not dramatic leaps, but cumulative refinements spread across millions of years. And yet, for all their progress, cynodonts remained overshadowed in their time. In the rivers, giant temnospondyls still lurked. On land, archosaurs were beginning to diversify. The cynodonts occupied niches of adaptability rather than dominance. Their success was measured not in flamboyance but in persistence. The very traits that may have seemed modest, whiskers, fur, upright gait, would eventually prove the most enduring. In retrospect, their quiet survival strategies were not temporary adaptations, but the seeds of a lineage that would outlast most others. Looking back, we are left with a haunting realization. The first fur and whiskers may have brushed against the dust of Pangaea unnoticed, their significance hidden from the creatures that bore them. No fossilized hair from that age has yet been found to prove it outright, and perhaps none ever will. But the skeletal clues, the comparative evidence, and the continuity of mammalian traits point toward their origin here. It is a reminder that some of the most transformative revolutions in life's history are not loud or obvious. They begin in the quiet, in small bodies beneath the shadows, in features that at the time meant only survival, but in the long arc of evolution became the foundations of everything to come. Who sees the empty land under the burning sun? In the silence after the Great Dying, when amphibians ruled rivers and cynodonts nosed through burrows, another group was beginning its slow, relentless climb. These were the archosauriforms, reptiles whose name simply means ruling reptiles in form, the early architects of a dynasty that would one day include dinosaurs, crocodiles, and pterosaurs. But in the early Triassic, they were only beginning to take shape, filling the barren interiors of Pangaea where other lineages faltered. Their bodies told a story of survival in extremes: powerful skulls, serrated teeth, sprawling yet robust limbs. They were animals built for hot landscapes and unstable ecosystems, stepping into roles left vacant by vanished Permian predators. The reveal is that their rise was not smooth or inevitable. Early representatives like Proterosuchus and Erythrosuchus did not look like masters of the future. They looked, frankly, awkward. Their anatomy caught in a halfway state between lizard-like ancestors and the more refined archosaurs that would come later. Proterosuchus, whose fossils have been found in South Africa and China, stretched about 3 meters long, with a jaw that curved down at the tip in an oddly hooked shape. Reconstructions often emphasize this drooping snout, which may have housed sensitive tissues or aided in seizing prey. Its stance was low, its gait still sprawling, but its teeth tell us it was a meat-eater. In a land with few competitors, even this imperfect body plan was enough to make it a formidable predator of the early Triassic floodplains. Erythrosuchus, discovered in South Africa and dating to the Middle Triassic, took this formula to grotesque extremes. Its skull could be nearly a metre long, out of proportion to its 4.5-metre body. With jaws armed with large conical teeth, it resembled a predator designed in haste, as if natural selection had emphasized head and bite above all else. The neck that supported this massive skull was short and thick, its limbs stout, giving the impression of a lumbering giant more than a sleek hunter. And yet, despite its unwieldy appearance, Erythrosuchus was among the top land predators of its time. Its fossils show up across floodplain sediments, suggesting that wherever rivers meandered across the arid Triassic landscape, this predator waited. The information we gather from these early archosauriforms is fragmentary, yet clear enough to mark a turning point. Unlike temnospondyl amphibians, these reptiles did not need water for reproduction. Unlike cynodonts, they did not remain small and marginal. They could stride farther into the interiors of Pangaea, into the sun-baked plains and desert basins where other groups could not follow. This gave them ecological opportunities denied to their competitors. The early Triassic climate was harsh, but archosauriforms were adapted to harshness. Their bones also reveal clues about physiology. Limb orientation in some species hints at a transition from sprawling to more upright postures, an innovation that would later define the full archosaurs. Upright stance meant more efficient locomotion, greater endurance, and the ability to hold bodies higher above the hot ground. The giant skulls of predators like Erythrosaucus suggest feeding strategies built on sheer power, but other archosauriforms were smaller, with lighter builds that foreshadowed the agility of later lineages. The early Triassic was a time of experimentation, with many branches exploring different possibilities, only some of which would endure. What made their rise possible was timing. With synapsids reduced in diversity and amphibians tied to wetlands, reptiles found space on the drier uplands. Their scaly skin, shelled eggs, and tolerance for aridity gave them an edge. They could nest away from rivers, forage in dry zones, and persist when seasonal droughts drove other creatures into decline. In the Great Reset of ecosystems, these advantages became decisive. By the Middle Triassic, archosauriforms were no longer just participants in recovery. They were beginning to define it. The resolution, however, is that even these pioneers were not invincible. Many early archosauriform lineages would vanish before the age of dinosaurs truly began. Proterosuchus and Erythrosaucus were not ancestors of crocodiles or dinosaurs directly, but side branches, experiments in body design that ultimately failed. Their legacy is not continuity, but possibility. They show us what it looked like when reptiles began to seize empty ground under the burning sun, reshaping ecosystems that had lain vacant since the Permian. The haunting question is how much of their rise was luck and how much was inevitability. Did the harsh climate of the early Triassic select uniquely for reptilian traits, making the dominance of archosaurs unavoidable? Or were these animals simply fortunate survivors, seizing a temporary window that could have closed differently had the dice rolled another way? All we can say with certainty is that in the dusty interiors of Pangaea, the first desert reptiles began their climb, and in their heavy skulls and awkward gaits lay the beginnings of a dynasty that would change the world. If we imagine the early Triassic interior of Pangaea, the picture is not one of lush forests or vibrant ecosystems. It was a land stripped bare, much of it open floodplains and parched deserts under searing seasonal heat. Into this emptiness stepped the archosauriforms, their scales protecting them from desiccation, their eggs tough enough to withstand dry conditions. Where amphibians clustered around shrinking pools and cynodonts burrowed for shelter, these reptiles could stride across open ground, claiming spaces no other vertebrates dared. In this way, their survival was less about dramatic innovation than about tolerating what others could not. The fossil record suggests they were opportunists as much as predators. Proterosuchus, with its downward-hooked snout, may have specialized in ambush hunting at the edges of rivers, snatching fish or small tetrapods. Erythrosaucus, grotesquely head-heavy, was built for overpowering rather than chasing, relying on crushing bites rather than pursuit. These were not elegant animals, but in a recovering world, elegance was unnecessary. Power, resilience, and the ability to occupy new terrain mattered most. Each discovery of these early reptiles serves as a reminder of how quickly ecosystems can reassemble after collapse, and how provisional those early steps often are. Archosauriforms show us bodies still in transition, awkward, sometimes ungainly, yet already experimenting with traits that would later become standard in reptiles. They were the first to stake claims on the deserts of Pangaea, leaving behind footprints and bones in sediments that still carry the heat of their ancient sun. When we study them today, what stands out is not that they were perfect designs, but that they were there at all, walking boldly into emptiness, shaping landscapes that had been silent for far too long. How do you rebuild buzzing life after a near-total collapse? In the early Triassic, when forests were sparse and rivers unpredictable, the silence of the air was almost as striking as the emptiness of the land. The Great Dying had not spared insects. In fact, evidence suggests that the Permian-Triassic boundary was marked by one of the most significant insect extinctions in history. entire orders vanished. Complex lineages that had thrived for tens of millions of years left no trace beyond that horizon. What followed was not an immediate recovery, but a long silence, a pause in which buzzing and clicking were rare sounds. It is difficult to picture a world without abundant insects, yet for millions of years after the extinction, this was the case. The reveal comes from the fossil record, which shows an abrupt decline in diversity at the end of the Permian. Some groups of primitive insects lingered, but the abundance of forms that had once thrived in Carboniferous swamps and Permian forests dwindled. Dragonflies, once rulers of the skies with wingspans over 1/2 metre, retreated into smaller, less frequent representatives. The complex guilds of detritivores, herbivores and predators collapsed. Fossilised plants from the earliest Triassic often lack the characteristic feeding damage we see in earlier and later periods, suggesting that for a time, plant leaves grew without the constant assault of insect mandibles. And yet, out of this silence, the insects eventually returned. By the Middle Triassic, new groups were appearing, groups that still dominate today. The true flies, or Diptera, can be traced back to this time, with their hallmark two-winged form already established. Their success lay in specialisation, rapid life cycles, flexible feeding habits, and the ability to exploit transient habitats such as decaying matter or ephemeral pools. Flies represent a model of resilience by being opportunistic, an evolutionary strategy that works well in unstable worlds. The beetles also weathered the storm. Coleoptera, with their hardened forewings forming protective cases over their bodies, had origins before the extinction, but emerged from it as one of the most diverse lineages. Their armoured design made them resilient to environmental stress, while their ability to exploit dead wood, dung, and carrion gave them an advantage in recovering ecosystems. By the Middle Triassic, they were diversifying into recognisable forms, and today, their legacy is extraordinary. 1 in every 4 described animal species on Earth is a beetle. That staggering proportion had its roots in these humble recoveries after global catastrophe. Perhaps the most profound innovation of the Triassic insect world was the rise of Hymenoptera, the lineage that would give us wasps, bees, and ants. Their earliest forms were small, sawfly-like creatures, plant feeders with simple wings and no stingers. But during the Triassic, something shifted. Some wasps began to adopt a new reproductive strategy, parasitoidism. Unlike parasites that live off hosts without killing them, parasitoids use other organisms as living incubators for their young, a grim efficiency that ends in the host's death. Fossils and molecular clocks suggest this strategy emerged in the Triassic, making parasitoid wasps some of the most influential predators of small invertebrates ever to evolve. By inserting eggs into spiders, caterpillars, or other insects, they created a control system that would ripple through ecosystems for the rest of geological time. The information we piece together from plant damage, insect body fossils, and amber inclusions tells us that the silence did not last forever. Bit by bit, buzzing returned. Leaf mines reappeared on plant fossils, showing that larvae were once again tunnelling through tissues. Tiny mandible marks tell of herbivory resuming. Wing impressions in sediments record the return of delicate flyers. By the late Triassic, skies that had once been silent now carried the drone of flies and the clatter of beetles, though never again quite like the world before the extinction. The resolution is that insect recovery was not just about numbers, it was about new strategies. Beetles with armour, flies with speed and flexibility, wasps with terrifying precision. Each innovation filled a gap left by vanished lineages, building an insect world that looks much more like our own. Yet the haunting question remains, why did it take so long? What conditions kept insects from rebounding immediately, and what invisible thresholds had to be crossed before their buzzing could resume? We may never fully know. But the evidence suggests that even for the most adaptable animals on Earth, recovery from the Great Dying was a slow and fragile process. A long silence before the familiar chorus of wings began again. The silence of the insects also had ripple effects that reached far beyond their tiny bodies. Plants, though capable of surviving without insect partners in the early Triassic, would have experienced a very different world without them. The near absence of herbivory meant that young leaves and shoots may have grown unchecked, but it also meant the cycling of nutrients slowed. Dead matter lingered longer without armies of beetles and larvae to grind it down. This delay in decomposition likely contributed to unstable soils and sluggish recovery of ecosystems. Forest floors that today would be alive with crawling, chewing, recycling activity might instead have been eerily still, with fungi and microbes carrying much of the burden that insects once shared. The same was true for the food web. Amphibians, reptiles, and early synapsids that might have relied on insects as prey were forced into alternative diets or narrower ranges. Fossil evidence shows a surprising scarcity of small insectivores in the earliest Triassic, consistent with the idea that their food base was diminished. This absence may partly explain why larger predators like temnospondyls and archosauriforms dominated. Ecosystems lacked the layered complexity that comes with abundant invertebrate prey. Until the buzzing returned, the chain of life remained truncated. By the Middle Triassic, however, the tide was turning. In deposits from sites in Russia, South Africa, and Germany, insect fossils become more common again. Winged forms leave behind impressions, and plant fossils once more bear signs of insect feeding. These traces remind us that recovery is often uneven and local. What was absent in one part of Pangaea may have been resurging in another. The first Triassic beetles, for example, appear in patchy distributions, hinting at refuges where they survived the extinction and slowly radiated outward. And when Hymenoptera began experimenting with parasitoid lifestyles, the entire ecological script shifted. Predation was no longer limited to jaws and claws. It extended to the cellular level, to bodies transformed into nurseries. This strategy did more than help wasps survive. It altered the population dynamics of other invertebrates, introducing new checks and balances into ecosystems. In a sense, the return of buzzing life was not just a recovery but a rewrite. The insect world that emerged after the silence was not the same as the one that vanished. It was leaner, more experimental, and full of innovations that still govern ecosystems today. So when we imagine the stillness of the early Triassic air, followed millions of years later by the faint hum of flies and the armoured crunch of beetles, we are hearing not just the return of life, but the sound of an entirely new world assembling itself one wing beat at a time. How soon did the oceans find a new apex predator? In the wake of the Great Dying, with reefs erased and marine ecosystems emptied of many of their giants, it might seem reasonable to expect a long delay before powerful hunters return to the seas. Yet within only a few million years, the fossil record shows us the sharp silhouette of a predator that cut its way back to the top, Birgeria. Among the earliest species recognized is Birgeria americana, described from Triassic rocks in what is now North America. These fish stretched up to 2 meters in length, with jaws lined by multiple rows of sharp conical teeth, some as long as 2 centimeters. For an ocean that had only just begun to recover from near-total collapse, this was a startling development. The seas had once again produced a hunter capable of ruling the waters. The reveal is that Birgeria was not some tentative experiment, but already a highly specialized predator by the early Triassic, around 249 million years ago. Fossil skulls and jaw fragments reveal a robust bite, and the arrangement of teeth shows adaptations for seizing slippery prey like fish. Unlike the blunt crushing dentitions of bottom feeders, Birgeria's jaws were built for slicing and holding. This suggests that active pursuit hunting had re-emerged surprisingly early in the recovery, at a time when much of the marine food web was still fragile. The story of Birgeria tells us something important about resilience in evolution. Large apex predators are often considered indicators of ecosystem stability because they rely on abundant prey. Yet here, so soon after global devastation, we already find evidence of them. How could a fish of this size and predatory specialization thrive so quickly? The answer may lie in the speed with which smaller prey species rebounded. Fossil assemblages from the early Triassic show swarms of small bony fishes and early ray-finned forms filling coastal waters. These schools would have provided rich hunting grounds for a fish like Birgeria, allowing it to expand into the vacant apex niche. The information from Birgeria fossils also reveals an evolutionary continuity. This genus would later diversify into several species across the Triassic seas, ranging from modest mid-level predators to giants over 4 meters long. Their global distribution from Europe to Asia to North America indicates they were successful colonizers of multiple marine environments. This pattern implies that their ecological role was not a local accident but part of a broader trend, the re-establishment of large predatory fish in oceans that had only recently been stripped bare. The significance of Birgeria americana lies not just in its size but in its timing. Only 3 million years after the Permian extinction, the appearance of a predator nearly as long as a human is tall forces us to reconsider how quickly ecosystems can reorganize. It suggests that ocean recovery was uneven. While corals lagged for over 10 million years, fish found ways to exploit new niches more rapidly. Apex roles did not remain vacant for long. They were seized by survivors ready to adapt. The resolution of the story is that Birgeria represents both fragility and resilience. Its very presence proves that ecosystems could rebuild faster than we might assume, but it also reminds us that apex predators are dependent on the stability of everything below them. Had the base of the food web faltered, Birgeria would have vanished without leaving its sharp teeth in the rocks. The haunting question is how many other predators briefly rose and fell during this unstable age, leaving no trace behind. Birgeria is the one we see, its teeth cutting through deep time to show us that even in the shadow of extinction, the oceans did not stay quiet for long. What makes Birgeria even more fascinating is the contrast between its sophistication and the backdrop it emerged against. In the earliest Triassic oceans, most communities were still threadbare. Reefs were absent, mollusks and brachiopods were diminished, and marine reptiles had yet to diversify into their iconic forms. Against this emptiness, Birgeria appears like a flash of premature ambition, a predator designed for abundance in a world still scraping together its food webs. The fact that it survived suggests that abundance was already returning, at least in patches. Shoals of smaller ray-finned fishes, quick breeding and adaptable, likely formed dense schools that swam near the coasts. These would have been easy targets, and a predator with speed and teeth could thrive on them. The bones of Birgeria also hint at a lifestyle that was not limited to one niche. Some species seem to have been coastal hunters, patrolling shallow waters where prey gathered in lagoons or estuaries. Others may have ventured farther offshore, suggesting versatility in their hunting. This ability to exploit multiple environments would have given the lineage resilience during a time of fluctuating seas and unstable climates. The teeth themselves tell perhaps the most compelling part of the story. Fossil jaws reveal multiple rows of sharp, recurved blades, angled in such a way that once prey was seized, escape would have been nearly impossible. Unlike the crushing dentition of shell feeders, Birgeria's bite was made for motion, grabbing, slicing, and swallowing whole fish. In a way, these teeth symbolize the return of motion to the oceans. After the stillness that followed extinction, when many ecosystems were reduced to simple forms and scavengers, the sudden reappearance of cutting predators marks a turning point. Movement, pursuit, and the dance of predator and prey had returned. And still, it is humbling to remember that Birgeria itself is not a direct ancestor of anything alive today. It belongs to a lineage of early ray-finned fishes that flourished for millions of years but eventually disappeared. Its success was real, but temporary. What its fossils give us is not continuity, but a window into how life improvises after collapse. Birgeria's teeth in Triassic stone are more than anatomy. They are markers of recovery, sharp edges reminding us that the oceans, though wounded, did not stay empty for long. The silence was brief. The seas found their teeth again. Why did so many reptiles try on the turtle shape? It is tempting to think of turtles as a singular invention, an evolutionary oddity that appeared once and never again. But the fossil record of the early and middle Triassic tells a more tangled story. In those barren landscapes and shallow coastal seas, multiple lineages of reptiles began experimenting with the same solution. A body plan shielded in armour, with limbs modified for slow but steady locomotion. These creatures were not all turtles in the modern sense, yet they were all playing with the same idea, as if nature itself was rehearsing the concept again and again. The reveal is that one of the earliest known proto-turtles actually lived before the Triassic. Unottosaurus from the late Permian of South Africa was not quite a turtle, but already displayed broadened ribs that formed a kind of partial shell. At about 30 centimetres long, it had a sprawling stance and a skull that still resembled other early reptiles, but its trunk was wide and rigid, suggesting the beginnings of the immovable torso that characterizes turtles today. Unitosaurus tells us that the turtle experiment began before the Great Dying, and somehow this idea survived the extinction bottleneck to flower again. By the late Triassic, we see the first unambiguous turtle, Proganochelys. About 1 metre in length, it possessed a fully formed shell composed of fused ribs and vertebrae on the top, the carapace, and a bony plate on the bottom, the plastron. Its head bore teeth along the palate and a beak at the front, and its tail was armed with spines. Unlike modern turtles, Proganochelys could not retract its head into its shell, but its protective armour was unmistakable. In less than 50 million years after the extinction, the turtle body plan had gone from tentative beginnings to its first successful version. Yet turtles were not alone. Alongside them swam the placodonts, a peculiar branch of marine reptiles. These animals, ranging from small durophagous feeders to bulky armoured forms, independently developed turtle-like shells. Henodus, one of the strangest, was about 1 metre long, with a flat, square shell and a beak-like mouth. Its body was adapted for a mostly aquatic life, its limbs better suited for paddling than walking. Fossils suggest it fed on plants and soft invertebrates in shallow lagoons. To look at Henodus is to see a turtle in silhouette, yet genetically it belonged elsewhere. Its shell was a case of convergence, a different lineage finding the same solution to survival. The information revealed by these repeated experiments with shells is striking. It suggests that in the unstable environments of the Triassic, dry lands punctuated by wetlands, shallow seas in flux, coastlines shifting under volcanic and tectonic forces, armoured, slow-moving animals found consistent advantages. A rigid body offered defence against predators, a low metabolism reduced food needs in harsh climates, and a beak plus crushing teeth allowed exploitation of hardy plants or shelled invertebrates. The shell, in other words, was not just armour. It was a multi-purpose innovation, protective, stabilising, and versatile. The resolution to this story is humbling. Turtles, of all these shell-bearers, are the only ones that endured beyond the Triassic. The placodonts vanished, their experiments left behind in stone. Unitosaurus remained a hint of a beginning rather than a direct ancestor. Henodus and its kin remind us that success in one era is not a guarantee of permanence. But the persistence of the turtle lineage tells us that among the many rehearsals, one version struck the right balance. The haunting question is why? Why this lineage and not the others? Was it simply timing, or some subtle advantage in physiology, reproduction, or behaviour that we cannot see in fossils? All we know is that by the end of the Triassic, the world had witnessed several attempts at the turtle shape. Only one would last. But for a brief moment, shells were everywhere, as if evolution itself could not resist trying the same design again and again. It helps to remember just how experimental the Triassic truly was. In the vacuum left by extinction, evolution seemed willing to try combinations that today look almost comical. Bodies stretched to absurd lengths, skulls reshaped into hammers or hooks, tails ending in claws, and shells appearing on creatures that were not turtles at all. The shell in particular seems to have been a recurring thought, surfacing again and again, as if natural selection kept circling back to it. For animals in shallow lagoons or along unstable coastlines, armour provided a kind of insurance. If speed could not guarantee survival, then perhaps protection could. Placodonts embody this logic. Some were modest in their armour, with broad rib cages and thick skin that offered a little extra defence. Others went further, layering dermal bone into plates that covered their backs like pavements of stone. The culmination of this trend was Henodus, whose broad, almost rectangular shell was so unlike the domes of true turtles that it seems like a separate invention altogether. When viewed from above, Henodus looked more like a floating raft than a reptile. Its body shape suggests it rarely left the water, perhaps browsing on vegetation or rooting in soft mud. The recurrence of shell-like adaptations in multiple reptile lineages highlights an important truth. Evolution is not a linear march toward predetermined designs. It is a constant testing of possibilities, many of which overlap in function even if their origins are different. Unitosaurus, Proganochelys, and Henodus were not part of a single story, but rather parallel experiments. They show that in the harsh landscapes of the Triassic, certain solutions kept being rediscovered, not because they were inevitable, but because they worked in that moment, and yet only one lineage carried the shell into the future. The others faded with the Triassic seas and coasts that shaped them. When we trace back the ancestry of modern turtles, we find a thread of continuity that passes through Progarnoculus, but we also see the ghosts of the other attempts preserved in stone. They remind us that what seems iconic today was once only one option among many, and that survival often depends on chance as much as design. The Triassic shell-bearers were many, but only one left descendants that still shuffle across beaches and dive through oceans today. Was this the world's first feather, or something stranger? Around 247 million years ago in the early Middle Triassic, an animal lived in the trees of what is now eastern France that forces us to ask that question. Its name is Myrasora grauvagerli, the wonder reptile preserved in fossils first collected by Louis Grauvogel in the Vosges Mountains before the Second World War. At first glance, Myrasora looked like a typical drepanosaur, part of a bizarre group of reptiles known for their grasping limbs, prehensile tails, and odd ecological roles. But down the middle of its back ran a crest unlike anything else known from its time, a row of feather-like appendages preserved in exquisite detail. For decades they were misunderstood or ignored. Only with modern preparation and synchrotron imaging did scientists realize that this was not just another odd reptile, but one carrying clues to the deep history of skin and its outgrowths. The reveal is in the structure of the crest itself. Each appendage was narrow and elongated, with a central ridge running along its length, giving them a feather-like profile in outline. But under the microscope, these structures lacked the branching filaments that define true feathers. There were no barbs or barbules. Instead, these were solid sheets of tissue, complex enough to defy simple comparison with scales yet not homologous to the feathers of birds or the hairs of mammals. Analyses revealed the presence of melanosomes, pigment-bearing organelles, similar in shape to those found in both modern feathers and fossilized bird plumage. Their presence suggests the crest was coloured, possibly dark or patterned, and likely used in visual signalling. Whether it was for mate attraction, intimidation, or recognition among members of its species, the crest was not a passive feature. It was a billboard of flesh and pigment. The ecological stage for Myrasora was the recovering forests of the Middle Triassic, some of the first woodlands to regrow after the devastation of the Permian extinction. Drepanosaurs were small, tree-dwelling reptiles with grasping hands and feet, often described as chameleon-like, though no exact modern analogue exists. Some even had hooked tails for clinging to branches. Myrasora's forward-facing eyes suggest an insectivorous diet, scanning bark and foliage for prey. In such a lifestyle, balance and grip mattered more than speed. Its crest, rising like a sail above its back, would have made it conspicuous in sunlight filtering through the canopy. This was not an animal built for hiding. The information we have from Myrasora shifts how we think about the evolution of skin coverings. For decades, scientists assumed that elaborate appendages, feathers, hairs, and similar structures were limited to the lineages that gave rise to mammals and birds. Reptiles, the story went, were creatures of scales, flat and simple. Myrasora challenges that simplicity. Developmental biology has shown that the genetic pathways capable of producing complex appendages go back at least to the Carboniferous, more than 300 million years ago. Myrasora is the first fossilized proof that such potential was realized outside the bird and mammal lines. Its crest represents an independent evolutionary experiment, parallel to feathers, but not ancestral to them. The resolution of the story is that Myrasora's crest reminds us that evolution is not linear and not parsimonious in its experiments. Feathers did not have to wait for dinosaurs to appear. Hair did not have to wait for mammals. Multiple lineages were tinkering with the same genetic toolkit, producing appendages that sometimes resemble one another in function and form, even when unrelated. Myrasora was not the ancestor of birds, nor did its crest survive beyond its own lineage. But for a brief moment in the Triassic, in forests still young after disaster, a small reptile carried a crown of flesh that showed just how inventive life could be. The haunting question that lingers is how many other such experiments were lost, never fossilized, their colours and shapes dissolving into deep time. For every Mirasaura we find, how many others never left a trace? We may never know, but the crest in stone tells us at least this much. The possibilities for life's skin have always been wider, stranger, and more colourful than we once imagined. The more closely we look at Mirasaura, the more it becomes clear that its crest was not a trivial ornament, but part of a broader evolutionary conversation happening in the Triassic. Across land and sea, animals were experimenting with display, armour, and structural novelties. Some reptiles stretched their necks to impossible proportions, others flattened their bodies into armoured rafts, and in the case of Mirasaura, the back itself became a canvas. These experiments tell us something profound about the pace of recovery. After the catastrophe of the Permian extinction, survival alone was not the end of the story. Once ecosystems stabilised enough to support more than the bare minimum, life began producing forms that were not just about staying alive, but about standing out. The crest of Mirasaura may have been used to impress rivals, or to signal species identity, but in any case, it points toward a world where communication and recognition were once again possible. This is why the presence of melanosomes in the preserved tissues is so extraordinary. Colour is often dismissed as a luxury in the fossil record, impossible to recover. Yet here, in delicate films of ancient tissue, tiny organelles survive that once held pigments. Their shapes resemble those in modern feathers that produce shades of black and grey. It is humbling to think that 247 million years ago, in forests reshaped by volcanic rains and early conifers, a reptile shimmered with colours that were not just functional, but expressive. Perhaps the crest caught light in ways that mattered to other Mirasaura, the way a bird's plumage does today. The discovery also widens our perspective on convergent evolution. For decades, paleontologists emphasised how unique feathers were to the dinosaur bird line, or how hair set mammals apart. But Mirasaura shows us that the genetic capacity for such elaborations was widespread and ancient. Developmental studies in living reptiles reveal that the same gene networks responsible for hair and feather growth also exist in scales. This means that with the right pressures and opportunities, a scaly reptile can push its skin into new forms. Mirasaura's crest was not a feather, yet it was feather-like, born from a similar toolkit expressed in a different way. We might be tempted to see such a creature as an evolutionary dead end, and in a sense it was. Drepanosaurs as a group vanished long before the age of dinosaurs reached its height. Yet dead ends matter. They reveal the experiments life was capable of, even if those experiments did not persist. In Mirasaura we glimpse an alternate world of possibilities, where reptilian lineages could have diversified into strange forms of ornamentation. Its discovery tells us that what we think of as rare innovations, feathers, hair, elaborate display structures, may have been cropping up far more often than the fossil record usually lets us see. And so, when we imagine Mirasaura clambering through branches with its prehensile tail, head tilting to reveal forward-facing eyes, crest fanned along its back, we should not picture an evolutionary mistake. We should picture a world that was beginning to dare again, to produce forms that went beyond mere survival. The wonder reptile's crest was not the first feather, and not the ancestor of anything alive today. But it was a reminder, etched into stone, that in the aftermath of disaster, life does not just rebuild, it experiments. And sometimes, those experiments are as strange and beautiful as any feathered bird or furred mammal yet to come. How long can you stretch a neck before it becomes a liability? The Triassic period offers one of the most extreme answers to that question in the form of Tanystropheus, a reptile that seemed to push proportionality past the limits of reason. Emerging in the Middle Triassic, Tanystropheus was not especially large by body length, roughly 2 to 6 meters in total, but nearly half of that length was consumed by a neck so absurdly elongated it defies casual comparison. With up to 19 cervical vertebrae, each stretched like a piece of pulled sugar, Tanystropheus carried a head no larger than that of a modest lizard on the end of a rigid pole several times the length of its torso. This configuration raises more questions than it answers. How did it walk? How did it feed? And why would natural selection favour such an ungainly design? The reveal is that Tanystropheus, despite appearances, was not a freak accident but a predator specialised for a very particular lifestyle. Fossils found in what is now Switzerland, Germany, Israel and China suggest it lived along coastal lagoons and shallow seas. Its teeth were sharp and conical, arranged for gripping rather than chewing, perfectly adapted to catch slippery prey such as fish or squid-like cephalopods. Reconstructions of its posture and limb structure indicate that it could function both in water and on land, but neither comfortably. On land, the immense neck would have been a burden, front-loading its balance and making rapid movement almost impossible. In water, however, that same neck allowed it to extend its head into schools of fish, while its body remained hidden among rocks or seaweed. Instead of lunging its entire body, Tanistropheus could simply swing its long neck like a fishing pole, snapping up prey before they even realized danger was near. The information revealed by modern studies complicates the picture further. CT scans of skulls have shown that Tanistropheus likely had multiple species or morphs, one smaller and more gracile, the other larger with heavier skulls. This suggests niche partitioning. Some forms targeted smaller prey in shallower environments, while others may have tackled larger fish in deeper waters. Even within a lineage that looked extreme to us, natural selection had carved out further subtleties. Yet with all its advantages, the neck came with inevitable vulnerabilities. A predator might use stealth and reach to hunt, but the long cervical series was also a weakness. A well-placed bite or strike from another predator could sever it. The rigid structure, lacking flexibility, limited how quickly Tanistropheus could maneuver. Its very specialization may have made it vulnerable to the unexpected. Comparisons with the plesiosaurs of the later Triassic and Jurassic underscore this tension. Like Tanistropheus, plesiosaurs evolved elongated necks, some even longer relative to their bodies. But plesiosaurs compensated with more vertebrae, greater flexibility and more powerful aquatic adaptations. Tanistropheus, by contrast, remained a compromise, not fully marine and not fully terrestrial, an experiment at the border of environments. Its neck was one of evolution's boldest gambles, and while it clearly worked for millions of years, it did not establish a lasting dynasty. The resolution to Tanistropheus's story is a reminder of how precarious extreme adaptations can be. The long neck gave it a unique window into ecological opportunities, allowing it to fish in ways few other reptiles could. But that same neck also marked its limits. Unlike turtles or crocodiles, its body plan did not persist into later eras. Instead, it leaves us with a haunting question. How often does evolution stretch a form to its breaking point, only to see it vanish, leaving behind a fossil puzzle that seems almost like parody? Tanistropheus looks strange to us, but it was real, successful, and perfectly suited to its time. And in that, it reminds us that the line between innovation and vulnerability can be impossibly thin. The first time paleontologists uncovered a complete Tanistropheus skeleton, they were convinced something was wrong. The neck bones seemed too long, too repetitive, as if an overeager preparator had spliced extra vertebrae into the fossil. For decades, reconstructions varied wildly. Some imagined a serpent-like swimmer, others a terrestrial ambusher dragging its unwieldy neck across dry ground. It took new finds in the 20th century, combined with careful anatomical work and eventually CT scanning, to confirm that the original vision was no mistake. This reptile truly carried an outsized neck, each vertebra elongated like a beam, stacking one after another until the head dangled improbably far from the body. Understanding how Tanistropheus lived requires setting aside modern analogies. No living lizard or crocodile carries such proportions, and even giraffes, often invoked in comparison, achieve their long necks in very different ways, with far fewer but more flexible bones. The vertebrae of Tanistropheus were rigid, locked together by interlocking processes that limited movement. Rather than a whip or a snake-like coil, its neck functioned more like a stiff pole. That rigidity may have been a feature, not a flaw. By keeping the neck straight, the animal could extend its head into schools of fish without telegraphing motion through a series of bends. A straight pole, suddenly thrust forward, would have been more efficient for a quick strike. Its skull reinforces the image of a fish specialist. The snout was narrow, the jaws lined with pointed teeth perfect for piercing slippery prey. The smaller species, perhaps no longer than 2 meters, would have focused on small fish and invertebrates in shallows, while the larger forms, some up to 6 meters, may have hunted deeper in lagoons where larger prey swam. In both cases, the strategy was the same: keep the heavy body hidden, project the head forward on that improbable lever, and let reach do the work. Yet this adaptation raises as many problems as it solves. A stiff, elongated neck is an obvious target for predators. Fossil evidence of bite marks on Tanistropheus bones suggests they were indeed attacked. A single strike could disable the animal. Moreover, the long neck imposed limits on locomotion. On land, the front heavy body must have been clumsy, forcing it to rely on short bursts rather than agile pursuit. In water, the stiff vertebrae prevented graceful turns. It is possible that Tanistropheus survived not by outmaneuvering competitors, but by occupying a narrow ecological slot few others attempted. When we compare it to the plesiosaurs that later inherited the seas, the difference becomes clear. Plesiosaurs, though similarly long-necked, evolved far more flexible cervical vertebrae and fully aquatic bodies with powerful flippers. They were not compromises, but specialists of the ocean. Tanistropheus seems almost transitional, caught between two worlds, testing a body plan that only later lineages would refine. It reminds us that the Triassic was less a gallery of perfected forms than a laboratory of trial and error. And so, when we look at the long-necked skeleton stretched across museum slabs, we are not seeing an evolutionary joke, but a serious attempt at survival. The fact that it lasted for millions of years shows that, however odd it appears to us, the strategy worked. What remains haunting is the sense that this adaptation was both ingenious and brittle. Evolution can create astonishing designs, but every design carries its weaknesses. Tanistropheus forces us to confront that truth with every elongated vertebra. How did synapsids fight back one last time with elephant-sized dicynodonts? By the Middle Triassic, synapsids had lost their stranglehold on terrestrial ecosystems. For more than 100 million years they had been the planet's dominant large vertebrates, from sail-backed predators like Dimetrodon to the tusked and burly herbivores of the Permian. But after the Great Dying, their ranks were reduced to scattered survivors. Cynodonts dwindled into burrowers and small omnivores. Amphibious therapsids clung to the margins. Most of the ecological power was shifting to archosaurs, the lineage that would soon produce crocodiles, pterosaurs and dinosaurs. And yet, in the floodplains of what is now Poland, the synapsids staged an improbable comeback. The reveal came in 2018 when paleontologists described Lisowicza bojani, a dicynodont so massive it rivaled modern elephants. Measuring more than 4 meters in length and standing nearly 3 meters tall at the shoulder, this Triassic herbivore may have weighed upwards of 15 tons. Until its discovery, dicynodonts were assumed to have been shrinking through the Triassic, confined to secondary niches. Lisowicza shattered that expectation. It showed that at least some synapsids were not only surviving but re-expanding, taking on the size and ecological roles that later would be occupied by dinosaurs. Dicynodonts were a peculiar group to begin with. Toothless except for a pair of tusks, they cropped vegetation with keratinous beaks, much like tortoises today. Their bodies were stout, their limbs upright rather than sprawling, and they were well adapted to life on open floodplains where bulk and endurance mattered more than speed. Lisowicza's bones, excavated from clay deposits in southern Poland, tell the story of a giant that grew quickly and lived in herds. Its limb structure suggests a fully erect posture, with legs held vertically beneath the body, a feature more associated with mammals and dinosaurs than with the sprawling reptiles of its day. The information hidden in its bones also forces us to rethink ecological balances in the Middle Triassic. Until Lisowicza, it was assumed that megaherbivory, plant eaters reaching elephant scale, was a phenomenon of the late Triassic dinosaur radiation. But here was a synapsid already filling that role, grazing and browsing on conifer forests, ferns and seed plants that were recovering across Pangaea. Its size alone would have deterred most predators, and its herding behaviour may have added another layer of protection. Where archosaurs were experimenting with body forms and diets, Lisowicza had chosen a strategy as old as it was effective: grow large, eat plants, and let mass itself be the shield. The resolution is bittersweet. Lisowicza represents both resilience and impermanence. It demonstrates that synapsids were not fated to vanish quietly. they could still rise to spectacular forms millions of years after near extinction. But it also stands as their last great gasp of dominance. By the late Triassic, archosaurs diversified into giants of their own, and dicynodonts faded from the record. Lysoetia leaves us with a haunting question. How many other brief resurgences, how many other lost dynasties came and went in those unstable millions of years, only to vanish before the fossil record could preserve them? The story of Lysoetia is less about synapsid failure than about the relentless shifting of power in deep time. Giants can return, but they cannot hold the stage forever. When the bones of Lysoetia first came to light in the Polish village of Lisowicz, they seemed almost impossible to categorize. At first glance, their sheer size led some to wonder if they might belong to one of the early dinosaurs. After all, who would expect a dicynodont, a group assumed to be dwindling into obscurity, to have left behind femurs and shoulder girdles comparable to those of elephants? Yet careful analysis of the skull fragments and tusks confirmed its identity. This was indeed a dicynodont, one of the same lineage that had once survived the Permian apocalypse by clinging to life in burrows and floodplains. The surprise was not that dicynodonts were still around. They had been found in Triassic rocks across several continents, but that one had taken such a bold leap back into the realm of the giants. What Lysoecia shows us is that recovery from mass extinction is rarely neat or linear. Groups written off as evolutionary has-beens can rebound in unexpected ways, filling niches we once assumed were the exclusive province of rising dynasties. The Middle Triassic was a time when ecosystems were still fluid, not yet settled into the patterns that would dominate later in the Mesozoic. In such a world, sheer size was a strategy available to any lineage capable of sustaining it. For Lysoecia and its kin, this meant adapting feeding strategies to exploit vast amounts of tough vegetation, conifers and cycads, that had grown back across the continental interior. With tusks for stripping bark and beaks for cropping stems, these animals could process what smaller herbivores could not. Yet the return of the giants also carried costs. Large body size demands enormous quantities of food and water. In an environment that could swing between droughts and floods, sustaining herds of elephant-sized dicynodonts would not always have been easy. Growth rates inferred from bone histology suggest Lysoecia grew rapidly, a strategy that may have helped it escape predation, but also meant that juveniles required a steady supply of resources. This balance between opportunity and risk highlights why such experiments sometimes flourish briefly and then disappear. They succeed when conditions allow, but when climates shift or competitors rise, the very scale that once offered protection becomes a liability. It is also humbling to consider the timing. Lysoecia appeared at roughly the same time archosaurs were beginning to diversify into their own larger herbivores. For a fleeting window, two very different lineages, one rooted in the ancient synapsid past, the other heralding the dinosaur future, shared the role of planetary megaherbivores. The fossil beds of Poland preserve that moment of overlap, a reminder that the succession of dominant groups is never clean-cut but layered, with old and new giants walking the same floodplains. So the rediscovery of dicynodont grandeur is not just about one species, it is a lesson in humility. When we assume a group has lost its evolutionary relevance, we may simply be missing the chapter where it tried once more to seize the stage. Lysoecia did not ultimately change the trajectory of the Triassic world, but it forces us to widen our imagination of what was possible. Synapsids did not quietly hand the crown to archosaurs. They wrestled for it, even if only for a little while, and left us the bones of an animal so massive it still defies expectation. In the silence of its extinction lies a question we can never fully answer. If conditions had tipped differently, could synapsids, not dinosaurs, have dominated the age to come? What if a planet used to drought suddenly drowned? For more than 15 million years after the Great Dying, Earth had settled into a rhythm of dryness. Pangaea's vast interior was dominated by desert belts, where seasonal monsoons brought little relief. Life had adapted to this aridity with drought-hardy plants, burrowing animals, and reptiles capable of soaking up heat without wasting water. But around 234 million years ago, that balance shifted violently. The world entered what geologists now call the Carnian pluvial episode. a brief but transformative interval when volcanic activity poured greenhouse gases into the atmosphere and the climate lurched from arid to saturated. The reveal comes from layers of basalt and sediments across Europe, China and the Americas. Enormous volcanic eruptions in what is now Western Canada spewed lava across landscapes and injected carbon dioxide into the skies. This sudden release of greenhouse gases destabilized the hydrological cycle. Evidence in lake beds and river deposits shows that regions once dominated by dunes and ephemeral streams gave way to permanent rivers and swampy floodplains. Fossil pollen reveals a dramatic turnover in plant life, with drought-tolerant species disappearing and lush conifer forests spreading. Rainfall did not just increase, it surged to levels that transformed ecosystems on a global scale. The information preserved in rocks and fossils paints a picture of ecological chaos. Sediments show repeated flood events, soils saturated with water, and the spread of freshwater systems where salt flats once existed. This climatic upheaval triggered extinction pulses in groups that had thrived in the arid early Triassic. Many specialized reptiles vanished, as did certain amphibians and plants tied to dry conditions. Yet at the same time, new lineages took root. Dinosaurs, previously minor players, expanded into niches opened by the decline of competitors. Early crocodile line archosaurs diversified as well, taking advantage of wetter environments. Even marine systems felt the change, with turnover in ammonites, bivalves and reef communities. For paleontologists, the Carnian pluvial episode is more than a curiosity. It marks a hinge in Earth's story, one of those turning points where a sudden climate shock opened the door for groups that would dominate the next 100 million years. Without these 2 million years of floods and storms, dinosaurs might never have risen to ecological prominence. The rains were not simply destructive, they were catalytic, reshaping landscapes and tilting evolutionary pathways. The resolution of this interval remains complex. After the rain subsided, Earth did not return to its previous dryness. Instead, the climate settled into a more humid equilibrium that would define much of the late Triassic. This left ecosystems permanently altered, with forests stretching across latitudes and river systems carving new habitats. The haunting question is how fragile Earth's balances have always been. One geological trigger, a flood basalt province erupting in what is now Canada, was enough to flip climates and reorder life across the globe. If 2 million years of storms could raise dinosaurs from obscurity, what other worlds have been built or lost in similar upheavals, their traces buried in stone? For millions of years, the Triassic world had been defined by dryness. Vast red sandstones and evaporate layers across what is now Europe, North America and China testify to sun-baked interiors where water was scarce and vegetation clung to the margins of rivers. Many of the survivors of the Great Dying had evolved under these parched conditions, from desert-adapted plants with thick seed coats to reptiles that could regulate their bodies under searing heat. Life had settled into this uneasy truce with the climate. Then, without warning, the ground itself betrayed them. In the Carnian stage, immense volcanic fields erupted across Pangaea's western rim. The Rangelia Large igneous province in what is now Western Canada belched out lava flows that eventually stretched for hundreds of thousands of square kilometres. With each eruption came vast plumes of carbon dioxide, sulfur dioxide, and other gases that rose into the atmosphere, disturbing global chemistry. The immediate effect was a greenhouse pulse, warming oceans, destabilizing air currents, and saturating the skies with moisture. Where once monsoon rains had been seasonal and predictable, now they became torrential, hammering landscapes unaccustomed to such floods. Geological layers capture the abruptness of this change. Red desert sandstones suddenly give way to grey mudstones, rich in plant debris and freshwater fossils. River systems shifted, carving new channels through floodplains that had never before held such volumes of water. Coal seams appear in places where swamps and forests suddenly flourished. Palynology, the study of fossil pollen, reveals dramatic turnovers, with many drought-tolerant plants declining while conifers surged, exploiting the wetter conditions. It is no exaggeration to say that entire ecosystems drowned and were replaced almost overnight in geological terms. This wet world brought both opportunity and disaster. Amphibians such as temnospondyls, once confined to shrinking waterholes, now found expanded wetlands to colonize, though many still could not cope with the instability of constant flooding. Some reptiles disappeared altogether, their desert-adapted lifestyles no longer viable. Insects too shifted, with fossil evidence of increased diversity among groups that thrived in humid, forested environments. Meanwhile, lineages that would define the rest of the Mesozoic, dinosaurs among them, began to spread into newly opened niches. Their rise cannot be traced to a single cause, but the timing of their expansion coincides uncannily with this soggy upheaval. The Carnian pluvial episode lasted only about 2 million years, a heartbeat in deep time, yet it permanently reshaped Earth's climate trajectory. When the volcanic eruptions waned and rainfall levels eased, the planet did not return to its former dryness. Instead, it settled into a more balanced but wetter regime that lasted through the rest of the Triassic. Forests expanded, rivers stabilized, and ecosystems carried the imprint of this watery interlude. The rains had not only extinguished but also created, leaving behind a world that looked very different from the one that had entered them. As we trace these changes in stone and fossil, we are reminded that Earth's climate has never been a stable backdrop. It is an actor in the story, capable of sudden and dramatic turns. 2 million years of rain may sound unimaginable to us, but for the Triassic world, it was enough to topple old lineages and hand opportunity to new ones. And it leaves us with an unsettling question. How many of life's turning points were not the result of slow competition, but of abrupt, climate-driven shocks that forced the world to reinvent itself almost overnight? Were these the first wings that never flew? Among the strange experiments of the Triassic, few are as debated or as misunderstood as Longisquama insignis. Known from slabs of rock collected in the late 20th century from Kyrgyzstan, this reptile was small, barely longer than a human hand, and in most respects unremarkable. Yet sprouting from its back were elongated appendages, flattened and blade-like, extending well beyond the animal's body length. They were not bones, nor ordinary scales, but something in between. Strange keratinous outgrowth that looked for all the world like oversized feathers, yet were not feathers at all. These bizarre structures have fueled decades of speculation about what evolution was attempting in this little Triassic creature. The reveal lies in their morphology. Each appendage was shaped like a leaf or a stiff feather vein, with a central ridge and thin lateral striations. Unlike true feathers, they showed no sign of branching into barbs or barbules, nor were they hollow like quills. Instead, they appear to have been solid and flat, perhaps supported by keratin and blood vessels, perhaps not. To some paleontologists, these were elaborate scales, modified through evolutionary tinkering into display devices. To others, they looked close enough to feathers that they might indicate a much earlier experimentation with the genetic toolkit that would one day give rise to plumage. If so, the roots of feather-like structures may stretch back tens of millions of years before the first dinosaurs ever carried them. But what were they for? The information is scarce, as only fragmentary fossils remain. Some researchers argue that the elongated scales acted as visual display, turning a tiny reptile into a walking advertisement to rivals or mates. Their size and position make them unlikely to have provided much insulation, and their stiffness suggests they were not flexible enough to be wings. One early hypothesis in the 1970s even suggested that Longisquama might have used them to glide, spreading the scales like parachutes. Yet this interpretation has not gained much traction, as the mechanics do not support efficient aerodynamics. More likely, they were a case of exaggerated display, a body saying, "Look at me," in the middle of dense Triassic forests. The resolution is that Longisquama may represent a dead end, an evolutionary flourish that dazzled briefly and then vanished. Its back appendages never developed into true feathers, and its lineage left no known descendants. Yet the haunting question is whether these structures point to something deeper, a genetic predisposition in reptiles for elaborating skin into complex appendages, one that could be tapped independently in multiple lineages. Mirasaura had its feather-like crest, Longisquama had its leaf blades, and later dinosaurs evolved true feathers. Each case appears to have arisen separately, suggesting that the potential for such structures was already latent in deep reptilian ancestry. Longisquama thus sits in the fossil record as a reminder of how messy innovation can be. Evolution rarely tests an idea just once. It throws prototypes into the world, some successful, others spectacular failures. The strange scales of Longisquama never lifted it into the skies, but they foreshadow the experiments in display and ornamentation that would one day explode into the riot of plumage in Mesozoic birds. And so, this tiny reptile entombed in stone from a forgotten valley leaves us with a mystery. How many other flamboyant prototypes existed in the Triassic canopy, their stories now lost, their strange adornments never seen again? By the time Longisquama was living in the middle to late Triassic forests of Central Asia, the world had already seen a burst of innovation in body coverings. The desert reptiles of the early Triassic had scales thickened for water retention. Myrasora had flaunted its strange crest of solid feather-like rods, and other small creatures had experimented with spikes, plates, and sails. In that broader context, Longisquama's extravagance does not look entirely out of place. It was one more entry in the long list of creatures testing what skin could be stretched, stiffened, or reshaped into. What makes it stand apart, however, is how uncannily its elongated scales resemble features we normally associate with feathers, despite being far removed from the lineages that ever developed them. The slabs that preserve Longisquama are frustratingly incomplete. The body is poorly known, and the head is missing, so we cannot say much about its diet or its ecological role with certainty. Most of our attention has focused instead on the dramatic dorsal appendages, some of which were longer than the animal's trunk. These elongated scales overlap in the fossil matrix like leaves pressed between pages, each showing a distinct midline and lateral striations. In life, they may have stood upright or fanned outward, creating the impression of a miniature palm frond sprouting from a reptile's back. One can imagine such an animal perched on a branch, its silhouette transformed by exaggerated banners that signalled presence from a distance. If they were used for display, then the question becomes, display to whom? Perhaps rivals of the same species, perhaps potential mates, or perhaps even predators. In many modern animals, elaborate structures serve multiple roles, broadcasting health and vitality to friends and foes alike. A brightly adorned lizard or bird often survives by convincing others it is not worth the chase. Longisquama may have been trying something similar. In a Triassic world filling with aerial insects, predatory reptiles and prowling archosaurs, looking larger or stranger could be a strategy worth the metabolic cost. What we cannot know is how flexible those scales were. Some reconstructions show them splayed out in a radiant fan, almost like the tail of a peacock. Others depict them stiff and parallel, forming a crest along the back. The truth may lie somewhere in between, and until more fossils are discovered, the debate remains unresolved. What is clear is that these appendages were not accidental growths. They were patterned and repeated with precision, a deliberate evolutionary investment. That means they must have conferred some advantage, however brief or localized. And here is where Longisquama becomes more than a curiosity. Even if its flamboyant scales never gave rise to feathers, they prove that reptile skin had the capacity to innovate far earlier and in more directions than we once assumed. Evolutionary biologists studying developmental pathways note that the same genetic signals that produce scales, feathers, and hair share deep similarities. Longisquama may represent one more tapping of that ancient toolkit, producing something that looked feather-like but followed its own path. In that sense, it is less an oddity and more a window into the hidden flexibility of reptile evolution. So as we trace the Triassic canopy, we begin to see a theme. Survival after mass extinction did not just mean filling empty roles, it also meant exploring new ways to be seen, to compete, and to attract. Longisquama may not have taken to the skies, but it carried on its back the seeds of an idea that skin could become spectacle that would echo in countless forms yet to come. Why do predators keep reinventing the crocodile body plan? By the late Triassic, around 220 million years ago, Earth's rivers and swamps had become home to some of the largest ambush hunters the world had ever seen. Their skulls were long and narrow, their bodies armoured with heavy osteoderms, their tails thick and muscular for propelling them through the water. They looked for all the world like crocodiles, yet these were not crocodiles. They belonged to a group called phytosaurs, an entirely separate branch of the reptile family tree that had independently converged on the crocodilian body plan tens of millions of years before the first true crocodilians emerged. Among them, giants like Smilosukos could stretch nearly 10 meters in length, making them the terror of Triassic waterways. The reveal is in the details. To an untrained eye, a phytosaur fossil looks almost indistinguishable from a crocodile's. But there is one crucial anatomical difference. In crocodiles, the nostrils are positioned at the tip of the snout. In phytosaurs, the nostrils sat far back, close to the eyes, sometimes even between them. This relocation gave phytosaurs an odd high-skulled look, but it did not diminish their role as stealth predators. They likely lay submerged with only their eyes and nostrils breaking the surface, waiting for fish, amphibians, or unlucky terrestrial animals to stray too close. Then, with a sudden snap of jaws lined with conical teeth, the prey was dragged under in a flurry of water and muscle. The information we have paints a picture of impressive diversity. Phytosaurs range from modest fish-eaters with slender snouts to hulking generalists with broad jaws capable of taking down large prey. Some species specialize so heavily that paleontologists can often identify diet from skull shape alone. Fossil trackways show they lived along riverbanks, lake margins, and deltas across what is now Europe, North America, India, and beyond. Their spread suggests they were among the dominant vertebrate predators of late Triassic freshwater ecosystems. But their story also highlights the curious pull of convergent evolution. Why did two unrelated reptile groups, separated by tens of millions of years, evolve into near-identical body plans? The resolution lies in ecology. The crocodilian design, elongated snout, low-slung body, armoured hide, powerful tail, represents a highly efficient solution to the problem of hunting at the water's edge. Any reptile lineage exploring semi-aquatic ambush lifestyles faced the same physical challenges, and natural selection steered them toward the same general form. Phytosaurs show us that the crocodile blueprint is less the invention of one lineage and more a recurring theme in reptile evolution. Yet phytosaurs did not survive forever. By the close of the Triassic during the End-Triassic extinction, they disappeared entirely, leaving the niche open for true crocodilomorphs in the Jurassic. The haunting question is whether their extinction was mere bad luck in the upheavals of climate and volcanism, or whether they were already ecologically redundant, holding on to a body plan that nature was destined to reinvent in another lineage. Their fossils remind us that even the most efficient designs can vanish, only to reappear in new hands, again and again across deep time. When we first meet the phytosaurs in the fossil record, it is during the later stages of the Triassic, a time when ecosystems were recovering from repeated shocks, yet also brimming with experiments in form. The rivers of what is now Western North America, for example, preserve entire graveyards of phytosaur skeletons lying among petrified logs and trackways of early dinosaurs. These assemblages tell us that these animals were not rare curiosities, but central fixtures of their environments. In many ways, they defined what it meant to live beside Triassic waters. If you were a small reptile or mammal-like cynodont venturing down to drink, the shadow beneath the surface was likely not a crocodile, but a phytosaur, eyes raised just above the ripples waiting for the briefest lapse in vigilance. What is striking is the speed with which phytosaurs seem to have risen to dominance. Within a few million years of their first appearance, they had already radiated into a variety of forms, from narrow-snouted fish specialists to massive broad-skulled predators like Smilosaucius that could challenge even the largest herbivores at river crossings. This rapid diversification hints at a landscape of open ecological space, the kind that follows extinction. Just as archosaurs were diversifying on land into early dinosaurs, Rauisuchians and ichthyosaurs, the phytosaurs seized the freshwater realm. The same evolutionary pressure that made archosaurs more upright and fast on land was steering their distant cousins into the water, where stealth and explosive ambush worked better than speed. Part of what fascinates paleontologists is how much the phytosaurs reveal about the power of convergence. They remind us that evolution is not random chaos, but a constrained dance, guided by the geometry of bones and the physics of hunting. Place a lineage into the murky shallows of a Triassic river, and given enough generations it begins to resemble a crocodile. The skull elongates, the body flattens, the tail deepens, and armor plates lock across the back. Even the behavioral script seems to repeat itself. Lie in wait, surge forward, seize with jaws, roll and drown. These are not merely crocodilian tricks. They are strategies discovered again and again by creatures separated by time and ancestry. Yet for all their success, phytosaurs lived on borrowed time. They were already locked into a body plan that, while efficient, may have limited further innovation. Unlike the archosaurs that would later evolve into true crocodilians, phytosaurs retained primitive ankle structures that restricted their movement on land. They could haul out, as the fossils of trackways suggest, but their design was best suited for water. When the world changed again at the end of the Triassic, when volcanic upheavals fractured Pangaea and poisoned rivers with sudden climate shifts, being too specialised may have become a liability. While dinosaurs expanded into new niches on land, and crocodilomorphs adapted with greater versatility, the phytosaurs faded into extinction. So when we look at a crocodile basking on a riverbank today, we are seeing not just one lineage's long survival, but the persistence of an ecological idea older than the dinosaurs themselves. Phytosaurs remind us that bodies can vanish, but blueprints often do not. They wait in the background, ready to be redrawn by evolution's hand when the circumstances are right. And that leads us to wonder, how many other body plans, now extinct, are still waiting for another chance to return? What arms race forced reptiles into spikes and shields? By the late Triassic, the world had become a proving ground for defence. Predators lurked not only in rivers, where phytosaurs reigned, but also on land, where rauisuchians and other large carnivores could crush smaller creatures in their jaws. In this unforgiving landscape, evolution produced a remarkable array of defences. Horns that curved forward like scythes, plates locked across backs like shields, and spikes jutting outward as if daring any attacker to take a chance. These were not ornaments alone, but survival strategies written into bone and skin. The reveal of this story begins with Shringosaurus, a horned reptile from what is now India, living about 230 million years ago. Its skull bore a pair of long, forward-curving horns, reminiscent of ceratopsian dinosaurs that would not appear until over 100 million years later. These horns were likely used not only to deter predators, but also in clashes between males, perhaps locking together in dominance contests much like the jousts of deer or antelope today. The rest of Shringosaurus's body was robust, with a strong neck to support the weight of the horns and powerful limbs that hint at a life spent both defending and competing. Its presence tells us that by this stage of the Triassic, reptiles were no longer content with simple speed or stealth. They were arming themselves visibly and dramatically. At the same time, other reptiles took a very different approach. The ichthyosaurs, such as Desmatosuchus, turned their entire bodies into fortresses. These herbivorous archosaurs were covered from snout to tail in heavy osteoderms, bony plates embedded in the skin that formed a rigid shell. In Desmatosuchus, some of these plates extended into sharp lateral spikes, creating a silhouette bristling with deterrence. At around 5 meters long, they were formidable not because of speed or attack, but because they were walking fortresses. Fossil trackways show they moved slowly along floodplains, digging for roots and tubers with their upturned snouts, safe in the knowledge that most predators would think twice before trying to wrestle them down. The information preserved in these fossils speaks of an escalating evolutionary contest. On one side were the ambush predators, phytosaurs in the rivers, rauisuchians on the plains, pushing prey to become less vulnerable. On the other side were the herbivores and smaller reptiles, forced to experiment with horns, plates and armour in order to survive. This arms race produced body plans that would echo far into the future. Horned skulls, armoured hides, and spiked silhouettes appear again and again in different lineages, from dinosaurs to mammals. The Triassic may have been the first stage where this defensive repertoire became truly widespread. The resolution of this story is haunting. Many of these armoured and horned reptiles did not survive past the Triassic. Shringosaurus and Desmatosuchus vanished, victims of the end-Triassic extinction. Yet their strategies were not lost. Later creatures would reinvent them, as if nature keeps certain solutions in reserve, waiting for the right ecological pressure to bring them back. Horns, plates and armour are reminders that survival is not only about being faster or stronger, but also about being harder to kill. And in a world that was still reeling from catastrophe, that may have been the wisest investment of all. As striking as Shringosaurus and Desmatosuchus appear in isolation, their existence makes more sense when placed within the broader ecological fabric of the late Triassic. By this time, Landscapes were no longer barren or sparsely populated. Forests of conifers and seed ferns shaded river valleys, and wetlands pulsed with amphibians, insects, and the first stirrings of true dinosaurs. Predators, freed from the constraints of earlier instability, grew larger and more specialized. In such a setting, any herbivore that ventured into the open was under constant threat, and natural selection favored those who carried their defenses with them. The horns of Shringosaurus, for instance, are not likely to have been mere ornaments. They were rooted deeply into reinforced bone, supported by strong musculature. Reconstructions suggest that males may have clashed head-to-head, not unlike modern goats or deer, testing one another's strength in contest over territory or mates. These confrontations would have left visible marks, worn horn tips, stress fractures, and perhaps even skull injuries that hinted a life lived in conflict. But beyond intraspecific battles, the horns also served as deterrents, a warning signal to any predator calculating the risk of an attack. A lunging Rauisuchian might still attempt the gamble, but the outcome was uncertain, and in evolution, uncertainty can be enough to shift the odds in favour of the defended. Desmatosuchus and its ichthyosaur kin present an entirely different philosophy. Their armour was not flashy, but comprehensive. The osteoderms across their backs formed interlocking rows, sometimes sculpted with ridges or knobs, creating both protection and perhaps even display patterns. The lateral spikes extended outward like a living barricade. For a predator, the choice of prey mattered. Chasing a lightly built synapsid might promise an easy kill, while tangling with a bristling wall of Desmatosuchus could mean broken teeth or torn flesh. The ichthyosaurs were also ecosystem engineers, rooting through soil and vegetation, leaving behind churned ground that opened niches for smaller animals and plants. Their armoured presence was not only defensive but transformative to the environments they inhabited. The proliferation of horns, plates and spikes also tells us that predator pressure was intense and varied. These defences were costly. Heavy armour slowed movement, large horns required significant metabolic investment, and spikes altered balance and gait. Such traits would not persist unless the threat of predation outweighed their burdens. In this sense, Shringosaurus and Desmatosuchus are evidence of the predators we often cannot see directly in the fossil record. Their very bodies bear testimony to a world where danger was omnipresent, where survival meant carrying the weapons of deterrence on one's skin. And still, there is a haunting undertone to their story. Neither horns nor shields proved eternal. Both Shringosaurus and Desmatosuchus vanished with the close of the Triassic, swept away by the volcanic convulsions and climatic chaos that reshaped the planet 201 million years ago. Their strategies, however, were not buried with them. Later epochs would see them return in new lineages: horned dinosaurs, armoured ankylosaurs, even mammals with antlers and tusks. It is as though the Triassic served as an early sketchbook, testing designs that would be refined and reimagined for millions of years to come. The arms race of the late Triassic was both a local struggle for survival and a rehearsal for some of the most iconic forms life would ever take. What did the very first dinosaurs actually look like? To answer that, we have to resist the temptation to project backward from the giants of the Jurassic or the famous icons of the Cretaceous. The earliest dinosaurs of the late Triassic were not thunderous sauropods or horn-faced ceratopsians. They were slender, lightly built creatures, often no larger than a human, whose bodies carried the seeds of future empires, but not yet the full weight of dominance. In their time, they were one set of contenders among many archosaur rivals, small threads woven into a complex tapestry of reptiles, amphibians, and mammal ancestors. The story of their dawn is one of cautious beginnings rather than instant triumph. When we pull the curtain back around 220 million years ago, in the arid basins of what is now the American Southwest, we meet Tawa Halai. Tawa was a graceful carnivore, about 2 meters long, with long hind limbs built for running and a skull lined with sharp teeth for seizing prey. Its bones were first unearthed in Ghost Ranch, New Mexico, in fossil beds that preserved multiple individuals together, suggesting that these early dinosaurs may have moved in small groups. Tawa belonged to the lineage of theropods, the same branch that would eventually give rise to the mighty tyrannosaurs and even birds, but in its own time it was more modest. It hunted small reptiles and early mammals, staying lean and agile in ecosystems crowded with larger, more dangerous competitors. Elsewhere, in South America, Another predator carved its place into prehistory, Herrerasaurus. At about 4 to 6 meters in length, it was one of the larger dinosaurs of its day, yet still dwarfed by contemporary Rauisuchians, the apex predators of the late Triassic. Herrerasaurus shows us how quickly dinosaurs began to experiment with body design. Its skull carried serrated teeth perfect for slicing flesh, and its hands bore sharp claws. Its hip structure, though still primitive in some respects, hinted at the innovations that would later allow dinosaurs to stand and move with such efficiency. Herrerasaurus was not a side note but a prototype, balancing ancestral traits with new solutions that would echo for millions of years. The fossil record of this time reveals that dinosaurs did not burst suddenly into dominance. They shared the landscape with ichthyosaurs, armoured herbivores that resembled tanks, with phytosaurs lurking in rivers, and with early crocodilomorphs testing their own designs for survival. In many places, dinosaurs were rare. Their bones make up only a small fraction of the fossils found in late Triassic layers. To stand in those ecosystems would not have felt like entering a dinosaur-ruled world, but rather one where dinosaurs were new experiments among many. The great twist is that these experiments held the key to the future. What made these small beginnings so important was a set of shared features that offered flexibility. Dinosaurs walked upright with limbs positioned beneath their bodies, unlike the sprawling gait of many reptiles. This gave them endurance and freed their lungs and muscles for more efficient movement. Their hips and ankles were stabilized for forward motion, making them both fast and resilient. Even in forms as early as Tawa and Herrerasaurus, these structural advantages were present. They may not have guaranteed success at once, but when global crises reshaped the playing field, these traits would prove decisive. We cannot say with certainty how dinosaurs behaved in these early stages. Did they hunt cooperatively, or did they stalk alone? Did they protect their nests or abandon eggs to the mercy of chance? The fossil record leaves us mostly with bones and trackways, and only hints of social behaviour. But what we do see is enough to suggest that they were not evolutionary accidents. They were already distinct, already charting a different course than their archosaur cousins. They were not yet kings of the Mesozoic, but they were writing the prologue. The haunting question that lingers is this: why was it dinosaurs, and not any of the other reptilian contenders, that eventually took the crown? Was it chance, timing, anatomy, or all of these at once? The late Triassic does not give us the full answer. It only shows us the moment when small, lightly built reptiles began to carry themselves in a way that would, much later, change the world. And perhaps that is enough of a lesson, that dominance does not always arrive with a roar, but sometimes begins with creatures no taller than a person, moving cautiously under the shadow of others, waiting for their time. To flow naturally into the rise of the first dinosaurs, it helps to step back and picture the world they emerged into. By the late Triassic, around 220 million years ago, the supercontinent Pangaea was still holding together, stretching nearly from pole to pole. Its interior regions remained dry and seasonal, marked by deserts vast enough to challenge any terrestrial life. Along the coasts and river valleys, however, vegetation had thickened since the early barren days, and ecosystems were once again bustling with a strange blend of survivors and newcomers. Amphibians still lingered in swamps, giant dicynodonts browsed in patches of vegetation, and the armoured ichthyosaurs trudged along floodplains. It was a patchwork of old and new, an unstable world in which evolutionary bets were constantly being placed. Amid this crowded field, the earliest dinosaurs were not guaranteed success. In fact, their bones appear so sparsely in many fossil beds that, for a long time, paleontologists debated whether they were marginal players or latecomers who happened to stumble into fortune. Yet their anatomy hints at something subtle, but profound. A way of moving and breathing that gave them advantages in speed, stamina, and energy efficiency. These were traits that mattered less in a world of ambush predators and lumbering herbivores. But in the long run, when climates shifted and ecosystems collapsed, they offered a kind of resilience that other reptiles lacked. Fossil trackways from the late Triassic give us additional insight into this quiet beginning. In sites across South America, North America, and even Europe, narrow-gauge footprints suggest small bipedal animals trotting efficiently across mudflats. These prints differ from the sprawling trackways of other reptiles, and though we cannot assign them with certainty to specific species, they fit well with the anatomy of early dinosaurs like Tawa or Herrerasaurus. To see those faint impressions is to glimpse not only individuals, but the possibility of herds or small groups, animals moving together across uncertain landscapes. Other archosaurs, however, were still formidable rivals. Rauisuchians, with their massive skulls and pillar-like limbs, occupied the top of the food chain. Phytosaurs patrolled the rivers with crocodile-like precision, snapping up prey that ventured too close. Even small crocodilomorphs were beginning to test out some of the body plans that would carry their lineage forward. Against this backdrop, the first dinosaurs seemed fragile, almost experimental, and yet, by existing alongside such competition, they were likely forced to sharpen their adaptations, exploiting niches that others could not fill. The real revelation of the late Triassic is not that dinosaurs were instantly dominant, but that they were adaptable. They were small enough to avoid drawing too much attention, fast enough to escape predators, and diverse enough to spread into different habitats. The fossil record shows carnivores like Herrerasaurus, but also hints of herbivorous and omnivorous relatives already branching off. This quiet radiation was less dramatic than the later dinosaur booms, but it was decisive. Evolution rarely favours the loudest or the largest immediately. It often favours those that can endure, wait, and seize opportunity when chaos returns, and chaos would return. Within less than 20 million years, the end-Triassic extinction would tear apart ecosystems once again, leaving many of these rival archosaurs behind. But the small, lightly built dinosaurs, creatures that began in the shadows of others, would endure and expand. Their dawn was not a sunrise that lit the world instantly, but a slow brightening on the horizon, almost unnoticed until the sky had already changed. Was the air claimed from the ground up or the trees down? That is the central question whenever we talk about the very first vertebrates that took to the skies. For hundreds of millions of years, the air had belonged exclusively to insects. Dragonflies with wingspans wider than a human hand had been patrolling wetlands since the Carboniferous, and beetles, wasps, and moth ancestors had already filled the skies of the Triassic with whirring wings. But sometime in the late Triassic, around 220 to 210 million years ago, a new experiment began. This time it was vertebrates, animals with backbones, that managed to lift themselves from the ground and remain there in sustained flight. These were the pterosaurs, the first true flyers among vertebrates, and their origin is still wrapped in uncertainty. The first fossils of pterosaurs discovered in the late 18th century seemed so strange that naturalists argued whether they were birds, bats, or reptiles. Today, we know they were reptiles, closely related to dinosaurs within the archosaur lineage. Yet even with centuries of study, we are still unsure of their exact ancestry. The fossil record of the late Triassic leaves us with tantalizing fragments, hints of small, lightly built animals that might have bridged the gap between ground-dwelling reptiles and the fully winged pterosaurs. One such candidate is Scleromochlus, a tiny reptile from Scotland no longer than a human hand. Its fossils show long hind limbs and a delicate body, traits suggesting it was a nimble runner, or perhaps even a hopper, like a kangaroo mouse. Some paleontologists see in Scleromochlus a potential ancestor of pterosaurs, reasoning that its strong legs could have been useful in powerful leaps that over time evolved into wing-assisted glides and then flight. Others remain cautious, pointing out that the fossils are incomplete and that resemblances may be misleading. Still, it gives us one possible glimpse of what an early ground-up flyer might have looked like. On the other side of the debate stands Charovipteryx, a reptile discovered in Kazakhstan. Unlike Scleromochlus, Charovipteryx did not look like a ground sprinter. Instead, it had extraordinarily elongated hind limbs, with membranes stretched between them and the body, forming a sort of delta wing configuration. Its forelimbs were much shorter, making it unlikely to have launched from the ground. Instead, it seems to have been a glider, leaping from trees and catching the air with its skin membranes. Some researchers have proposed that Charovipteryx represents a trees-down experiment in aerial locomotion, perhaps related to pterosaurs, though others argue it may simply be an evolutionary oddity without direct descendants. Whichever path the pterosaurs took, Whether bounding upward from the earth or gliding downward from the canopy, the end result was revolutionary. By the late Triassic, true pterosaurs like Eudomorphodon were already in the skies of Europe, sporting wingspans of about a metre and jaws lined with needle-like teeth perfect for catching fish. Their anatomy shows the hallmark of the group, a dramatically elongated fourth finger, stretched to support a membrane of skin that formed the wing. Their bodies were light, their bones hollow, and many carried crests or ridges on their heads that might have helped with display or aerodynamics. These were not halfway flyers or gliders, they were fully adapted for life in the air. The very presence of pterosaurs in the late Triassic raises more questions than it answers. How quickly did they evolve from small, earthbound ancestors into skilled flyers? Did they initially compete with insects for food, or were they primarily fish hunters along coasts and rivers? And how did their early forms survive in ecosystems dominated by large terrestrial predators and aquatic ambush hunters? We cannot say with certainty, but the fossils suggest that their lightweight bodies and aerial lifestyle gave them a niche few others could touch. The emergence of pterosaurs also tells us something deeper about evolution's creativity. Flight had already been invented by insects hundreds of millions of years earlier, and it would be reinvented again later by birds and then bats. Each time the solution was different, yet each time it opened up vast new opportunities. For pterosaurs, wings meant they could escape many predators, travel long distances to find food, and perhaps colonize environments too scattered for terrestrial animals. Their flight was not just a trick of anatomy, it was a passport to new worlds. And yet, for all their innovation, the earliest pterosaurs were not giants. They were small, fragile-looking creatures whose wingspans might not have exceeded a metre or two. They were vulnerable, dependent on the survival of the delicate wing membranes and hollow bones in a dangerous world. It would not be until much later, in the Jurassic and Cretaceous, that their lineage would produce giants that rivaled small aircraft. In the Triassic, the story was one of tentative beginnings, of fragile sails catching the wind above landscapes still scarred by extinction. The haunting question that follows is this: was it inevitability or pure chance that gave reptiles the sky? Could another lineage of gliders have made the leap instead, leaving us with a world where flight belonged to an entirely different kind of creature? The fossils do not answer that. They only remind us that in times of ecological upheaval, opportunities appear, and life is never shy about seizing them in forms we may find strange or wondrous. The air of the late Triassic was not empty, of course. It was already alive with the whir of insect wings. Flies, beetles, moth ancestors, and wasps had claimed the skies tens of millions of years earlier. To lift a vertebrate body into that same space was something altogether different. Insects weighed almost nothing and could be powered aloft by thin sheets of chitin. Vertebrates carried bones, muscles, and organs, a heavy burden compared to their tiny insect contemporaries. To conquer the air under those circumstances required more than a simple leap. It required rewriting the architecture of the body itself. Pterosaurs did just that. Their wing membrane stretched not between all four limbs, as in bats, but across an elongated fourth finger, an extraordinary modification that no other animal has ever used for powered flight. Supporting such a design demanded hollow bones to reduce weight, powerful chest muscles to drive the wings, and a reorganized respiratory system that may have already resembled the flow-through breathing of modern birds. These changes did not happen all at once. They must have accumulated in earlier forms, small, lightly built archosaurs experimenting with climbing, gliding, or sprinting in ways we can only guess at. Each fossil we find is like a single frame torn from a film we can no longer watch in sequence. It is tempting to imagine these first flyers launching over lakes at dusk, chasing swarms of insects that hovered in the warm air. Their delicate jaws, lined with sharp teeth, suggest a diet of fish, but insects could have offered a ready supplement, especially for smaller forms. Their keen eyesight, indicated by the large eye sockets in many skulls, would have made them skilled hunters from above. What is most striking, however, is how quickly they seem to appear in the record already perfected for flight. By the time we meet Eudomorphodon in Italy, or Carnidactylus in Austria, they are unmistakably pterosaurs, not halfway creatures fumbling at the edge of gliding. That suddenness hints at ghost lineages, ancestors we have not yet found, perhaps still waiting in rocks that have not been opened. The debate about whether flight arose from the ground up or the trees down may never have a final answer. Scleromochlus offers a plausible runner, Charovipteryx a plausible glider. Both may be telling us partial truths, snapshots of parallel experiments in aerial life. Evolution often tests multiple paths at once, with only some reaching stable solutions. What matters is not whether one model was correct and the other wrong, but that in the chaotic recovery world of the Triassic, the air itself became another arena for adaptation. Seen in this way, the first pterosaurs were not just reptiles with wings, they were pioneers of a new ecological dimension. Once the sky was open to them, it remained theirs for over 150 million years. That immense tenure, longer than the entire existence of our own species, began with these small and vulnerable flyers of the Triassic. Their wings carried them above a dangerous Earth, but also into evolutionary history, where they remind us that even in the aftermath of catastrophe, life always finds new directions to explore. How did ichthyosaurs invent the dolphin body plan millions of years before dolphins themselves existed? It is one of the great stories of convergence in evolutionary history. On the surface of it, there is something uncanny about finding the streamlined silhouette of a modern porpoise in the rocks of the late Triassic, a time when mammals were still mouse-sized creatures burrowing in the shadows. Yet, there it is, in fossils pulled from mountains that were once ocean floors, a reptile body transformed into a torpedo shape, with a beak-like snout, a fin on its back, and flippers in place of legs. These were the ichthyosaurs, fish lizards, in name but in truth neither fish nor lizard. They were reptiles that went to sea and never came back. The first step in understanding them is to look further back than the Triassic seas. For decades, paleontologists assumed that ichthyosaurs originated in the chaotic recovery after the Great Dying, diversifying quickly into marine specialists. That story was already compelling. Reptiles pushed into the water by collapsed land ecosystems, finding opportunity where extinction had opened ecological doors. But in 2023, a fossil from Svalbard pushed the timeline deeper. There, in rocks laid down in the very latest Permian, scientists uncovered what appears to be a fully marine ichthyosaur. If that interpretation holds, then ichthyosaurs not only evolved before the Permian extinction struck, but managed to survive it as well as the Triassic crises that followed. If so, then their streamlined form was not a sudden improvisation of disaster, but a tested design resilient enough to pass through two global cataclysms. By the Middle and Late Triassic, ichthyosaurs were no longer tentative experiments. They had diversified into an array of forms, from slender fish-eaters to immense plankton strainers. One of the most impressive was Shastasaurus, discovered in what is now California. At lengths of 20 to 23 meters, these giants rivaled anything else in the Triassic seas. They lacked the fearsome teeth one might expect in a predator that size. Instead, their jaws were toothless or lined only with tiny vestiges, suggesting they may have been suction feeders, pulling squid and soft-bodied prey into their cavernous mouths. The very presence of an animal that large so soon after Earth's greatest extinction speaks to how quickly ecosystems were rebuilt and how stable they became in parts of the Triassic oceans. Even Shastasaurus, however, has now been surpassed in size. In 2020, a young fossil hunter in the United Kingdom stumbled on a jawbone fragment so large that it could not be matched to any known ichthyosaur. Careful analysis revealed it belonged to a new species, later named Ichthyotitans severnensis. At an estimated length of 25 meters or more, it would have rivaled today's blue whale, the largest animal ever to live. To think that such giants were already in the seas of the late Triassic is staggering. It suggests that marine ecosystems had recovered enough productivity to support animals at the very limits of what the vertebrate body can achieve in size. What made ichthyosaurs so successful was not simply their size, it was their body plan. Streamlined for speed, with crescent-shaped tails for propulsion and fins for steering, they converged on the same solutions later found by tuna, sharks, and dolphins. The physics of water has only so many ways to allow fast, efficient swimming, and evolution arrived at this particular solution multiple times. But ichthyosaurs were the first vertebrates to perfect it. In their time, they ruled the seas as apex predators and giants alike. Their fossils also tell us about their biology in ways that make them feel surprisingly modern. Some specimens preserve traces of skin impressions showing smooth, scaleless bodies, much like whales. Others reveal evidence of live birth, with embryos still inside fossilised mothers, showing that ichthyosaurs, like whales, had severed their dependence on land entirely. A few skeletons preserve stomach contents, including fish bones and squid hooks, frozen in the act of digestion for 200 million years. These details remind us that behind the grand statistics of mass extinctions and recoveries are living creatures with life cycles, appetites, and behaviours not so different from marine animals we know today. Yet for all their success, ichthyosaurs were not permanent fixtures. By the end of the Triassic, some of the largest forms began to disappear, perhaps victims of the climatic upheavals and oceanic anoxia that struck again around 201 million years ago. Others would persist into the Jurassic and even into the Cretaceous, diversifying once more before fading from history. Their story, then, is both one of triumph and of limits. They show us how quickly life can invent radical new forms, but also how even the most successful experiments are vulnerable when Earth shifts under them. The haunting question that lingers is this: did ichthyosaurs reach the absolute ceiling of marine vertebrate evolution, only to vanish, leaving whales to reinvent their role tens of millions of years later? Or were they simply another reminder that no matter how perfect a body plan seems, survival is never guaranteed in a world as restless as ours? To appreciate just how remarkable the ichthyosaurs were, we have to pause and imagine the world into which they swam. The late Triassic seas were not empty expanses of blue. They were layered with challenges, low oxygen zones in deeper waters, blooms of plankton that came and went with climate swings, and a cast of marine reptiles that were only beginning to establish their place in the food chain. Against this backdrop, ichthyosaurs not only survived but thrived, adapting with a speed that is still puzzling to paleontologists. How did they evolve from land-walking ancestors into hydrodynamic specialists in such a short geological window? The fossil record is still incomplete, but what we have suggests that once their lineage committed to the ocean, natural selection pushed their bodies towards streamlining at a pace that feels almost abrupt. When we look at their skeletons, it is clear that ichthyosaurs had fully embraced a marine identity. The transformation of limbs into stiff paddles is perhaps the most striking feature, a reminder that land was no longer part of their daily existence. Unlike turtles or seals, there is no indication they ever came ashore. Even reproduction happened in the water, as fossilised mothers with embryos preserved inside demonstrate. In this sense, ichthyosaurs pioneered an entirely oceanic lifestyle tens of millions of years before whales repeated the same experiment. It is a convergence so precise that one could mistake their silhouettes for cetaceans, if not for the reptilian skulls and spines that betray their true identity. The diversity of ichthyosaurs in the Triassic also tells us something about the resilience of marine ecosystems after the Great Dying. The presence of small, agile hunters alongside leviathans like Shastasaurus or Ichthyotitan suggests that the food web was already rich enough to sustain multiple feeding strategies. Filter feeders likely strained soft-bodied cephalopods, while toothy species chased fish and ammonites. Apex predators needed a cascade of smaller prey beneath them, and the fact that such giants could reach whale-like proportions indicates that life in the Triassic seas was not simply recovering but flourishing. And yet, their very success makes the silence of their eventual decline more poignant. By the time the Triassic closed with another extinction pulse, many of the largest ichthyosaurs had disappeared. Was it sheer size that made them vulnerable, too dependent on stable food supplies in a world that was anything but stable? Or was it simply a case of ecological turnover, where the same geological forces that opened niches for their rise also sealed their fate? We cannot say for certain. All we know is that ichthyosaurs endured through 2 mass extinctions, achieved body sizes rivaling the greatest animals of all time, and then dwindled until they too became ghosts of stone. Their story flows naturally into a broader reflection on the Triassic itself. Here was a period that began in near sterility, scarred by the loss of 90% of species, and yet within a geological heartbeat produced forests, insects, amphibian giants, reptile experiments, early dinosaurs, and whales before whales. If the Triassic feels chaotic, it is because chaos was the only path forward. And amid that chaos, the ichthyosaurs remind us that sometimes life runs so far ahead of the curve that it sketches the outlines of futures not yet possible. Millions of years before dolphins broke the surface of the ocean, something very much like them was already there, proving that form follows function across time as well as space. What happens when a planet that has already staggered back from the brink is forced to endure another hammer blow? The Triassic was a time of recovery, invention, and extraordinary evolutionary experiments, but its final act was not one of gentle continuity. Around 201 million years ago, Earth entered another crisis. This time it was not a comet strike or a sudden collapse of ecosystems, but an eruption that seemed to have no end. Lava poured from the Earth for hundreds of thousands of years, building a province of igneous rock so vast it would eventually stretch from modern North America to Africa, and its consequences were catastrophic. The story begins with the slow rifting of Pangaea. For tens of millions of years, the supercontinent had remained intact, spanning pole to pole. The tectonic plates are never still, and deep beneath the crust, stresses were mounting. By the late Triassic, fault lines had begun to spread across the landmass, the early outlines of what would one day become the Atlantic Ocean. As continental plates pulled apart, enormous plumes of magma rose from the mantle, tearing open fissures thousands of kilometres long. What followed was the emplacement of the Central Atlantic Magmatic Province, one of the largest volcanic events in Earth's history. The eruptions were not a single apocalyptic blast, but a drawn-out episode of fire and ash that endured for something like 600,000 years. To grasp that scale, it helps to picture the lava fields themselves. The flows covered an estimated 10 million square kilometres, an area larger than modern Europe. Sheets of basalt piled hundreds of metres deep, blanketing landscapes that had once been forests and floodplains. Each pulse of lava released staggering volumes of gases into the atmosphere: carbon dioxide, sulfur dioxide, and other volatiles that disrupted climate systems already stretched thin. Models suggest that carbon emissions from these eruptions rival anything released by the fossil fuel industry today, but spread over geological time. Even so, the effect was profound enough to trigger runaway greenhouse conditions, destabilizing ocean chemistry and thinning the oxygen that marine organisms depended upon. The fossil record captures the consequences with chilling clarity. Roughly 76% of all species vanished in this interval. Marine ecosystems that had rebuilt themselves after the Permian extinction collapsed again as oceans became stratified, their deep layers starved of oxygen. Ammonites, conodonts, and reef builders were hammered by the dual stress of warming and anoxia. On land, many reptile groups that had flourished in the Triassic, phytosaurs, yetosaurs, and certain synapsids, disappeared entirely. Plants suffered localized crashes as shifting rainfall patterns and higher temperatures pushed some species past their tolerances. The extinction was not instantaneous, unfolding instead in pulses that may correspond to distinct eruptive phases. Each wave of lava and gas drove ecosystems into deeper crisis, until what remained were those lineages resilient enough to withstand repeated shocks. Among the survivors were the dinosaurs. Their resilience is still debated. Some paleontologists argue that they were simply lucky, their small and diverse early forms positioned in niches that buffered them against sudden change. Others suggest that physiological traits such as rapid growth, upright posture, or efficient respiration gave them a competitive advantage. Whatever the reason, they passed through the bottleneck when so many contemporaries did not, and the stage was cleared for their spectacular radiation in the Jurassic. It is tempting to read inevitability into that outcome, as though dinosaurs were destined for dominance. But the truth is humbler. Their rise was enabled as much by catastrophe as by adaptation. What remains difficult to reconstruct is the lived experience of the extinction. How did a world unravel over 600,000 years? Imagine forests periodically drowned in lava, rivers cut off by basalt walls, skies hazed with ash and sulfur that dimmed sunlight and turned rain acidic. Imagine oceans slowly losing their breath as carbon dioxide levels rose, suffocating fish and reptiles alike. These were not isolated disasters, but a repeating rhythm of collapse and brief recovery, collapse and recovery again, until the biosphere itself was transformed. The Central Atlantic Magmatic Province endures today as weathered ridges and cliffs across 4 continents, a stone reminder of a time when the planet remade itself in fire. Its legacy is paradoxical. It annihilated much of Triassic life, yet it also set the stage for the ecosystems of the Jurassic. Without this drawn-out catastrophe, the familiar dinosaur-dominated worlds of later prehistory might never have come to be. It leaves us with a question that science can never fully answer. When we look at extinction, do we see the end of possibility, or the clearing of space for futures we cannot yet imagine? Even after the last of the great lava flows cooled, the world did not reset overnight. The basalt fields that had smothered entire valleys remained barren for centuries, their surfaces too hot, too unstable, too chemically harsh for roots to take hold. Only after weathering began to break down the volcanic rock into soils could plants cautiously reclaim the land. In some regions, fossilized pollen tells us that ferns were among the first pioneers, their spores able to spread widely and germinate in thin soils. They formed low carpets across cooling lava plains, the first step in the long, uneven process of recolonization. Behind them came conifers and other seed plants, weaving forests back together, though often in patchy mosaics that hint at repeated setbacks. The oceans faced an even slower recovery. When carbon dioxide floods the atmosphere, it eventually dissolves into seawater, where it lowers pH and reduces oxygen solubility. For millions of years after the Central Atlantic magmatic province eruptions, many marine basins remained stratified, with oxygen only in the surface layers. Deep waters were anoxic, sometimes even toxic with hydrogen sulfide, conditions that would have limited the diversity of marine life. Some groups of ammonites managed to survive, but their diversity was sharply reduced. Corals, which had already endured a long absence earlier in the Triassic, once again struggled to re-establish themselves, and reef building would not reach its later Jurassic flourish until climates stabilised. The extinction left visible gaps in the fossil record that speak to how difficult it was for ecosystems to stitch themselves back together. For vertebrates on land, the balance of power had shifted permanently. The phytosaurs, once dominant along Triassic rivers, were gone. Ichthyosaurs, those heavily armoured herbivores, disappeared too. Many synapsid lineages dwindled or vanished. What remained were early crocodilomorphs, and, most decisively, the small and lightly built dinosaurs. The record suggests that in the wake of the extinction, they diversified rapidly, spreading across Pangaea's fractured landscapes. With rivals removed, they claimed niches as herbivores, omnivores, and predators. This was not the first time reptiles had surged forward after a crisis, but it was the time that would stick. From this point onward, dinosaurs would dominate terrestrial ecosystems for the next 150 million years. The Central Atlantic magmatic province did more than extinguish it, reshaped the Earth itself. The rifting it heralded would, over tens of millions of years, widen into the Atlantic Ocean, permanently altering the map of the planet. In a sense, the end-Triassic extinction marks the moment when the old Pangaean world truly broke apart. Life, as always, adjusted to the new geography. Rivers, deltas, and coastlines were redrawn, and with them the distribution of plants and animals. The Triassic, that age of recovery and experiment after the Great Dying, gave way to the Jurassic, remembered as the golden age of the dinosaurs. Yet the deeper lesson of the Central Atlantic magmatic province may be one of fragility. Twice in 50 million years the Earth had experienced mass extinctions that wiped away most of its species. The Permian had nearly ended complex life altogether. The Triassic's finale showed that even after a long recovery, ecosystems could still be undone by forces from beneath the crust. Our understanding of these events remains incomplete. We know the broad outlines, the lava, the gases, the extinctions, but not the precise details of how each pulse of eruption cascaded through food webs, or why certain lineages clung on while others faded forever. Science offers glimpses, but the full lived experience of that ancient catastrophe is lost. And perhaps that is the most haunting part. When we look at the black basalt ridges of Morocco, or the cliffs along the eastern seaboard of North America, we're not just looking at frozen lava. We're staring at the ruins of a world, a silence written in stone. The Triassic ended not with a single bang, but with a drawn-out fire that lasted 600,000 years, long enough to erase most of what evolution had built, yet just short enough to clear space for something new. It leaves us with a question worth carrying. How many futures are buried? What strange creatures were lost forever at the threshold of the dinosaur age? To close the Triassic story, we have to look back across 50 million years and see it not as a straight path toward dinosaurs, but as a world of experiments that never repeated themselves. It was an acid trip of nature, a frantic improvisation after the Great Dying, and many of its actors left the stage for good. When the final volcanic upheavals reshaped the continents around 201 million years ago, they did more than remove 3/4 of living species. They silenced lineages that had carried entire ecosystems on their shoulders and left behind only traces in stone, strange fossils that remind us how provisional survival really is. The amphibians that once towered in swamps with skulls 4 feet long, animals like Mastodonsaurus or Plagiosaurus, were gone. They had ruled the floodplains in the aftermath of the Great Dying, dominating because reptiles were slow to adapt. Yet they proved vulnerable to the changing climate and to the relentless competition of new reptilian predators. Their extinction left no direct heirs, only the faint lineage that would one day give rise to frogs and salamanders. Whole way of being, giant amphibians as apex river hunters, disappeared with them, a strategy that never returned. Equally haunting are the reptile lineages that tried, failed, and left only questions. Drepanosaurs with their prehensile tails and grotesque claws, creatures that seemed half bird and half chameleon, vanished without leaving successors. Longisquama, flashing its flamboyant scales that might have mimicked feathers, was extinguished. The odd placodonts like Henodus, with flat shells that resembled turtles but were not turtles, never reappeared. Even the mighty phytosaurs, rulers of rivers with jaws so crocodile-like that for years they were mistaken as ancestors of crocodiles, were obliterated. Their body plan had been perfected for ambush, their dominance nearly guaranteed, and yet they were erased, while crocodiles proper, still small and unimpressive in the late Triassic, survived. The irony is stark. Convergence was not protection. The ichthyosaurs remind us of another kind of fragility. They had raced ahead of evolution, inventing the dolphin body plan before dolphins were even conceivable. They reached sizes rivaling whales. They gave birth at sea. They filled every marine niche. Yet the very largest, the leviathans like Shastosaurus and Ichthyotitan, disappeared at the end of the Triassic. It was as though the world could not sustain giants in the face of sudden volcanic upheaval. The smaller ichthyosaurs survived into the Jurassic, but their titanic kin were gone forever, proving that even the most successful experiments can be undone by global accident. It is tempting to see the Triassic as a preamble, a rough draft leading toward the so-called Age of Dinosaurs. But that would be unfair to the dozens of lineages that lived, thrived, and died within it. For them, the Triassic was not a rehearsal. It was the only performance they would ever give. Nature's acid trip was not a practice run. It was real, and for many, final. The end of the Triassic shows us something humbling about survival. Dinosaurs did not emerge because they were destined to. They endured because they happened to carry the right mixture of traits when catastrophe struck. Upright postures, rapid growth, perhaps flexible metabolisms, all of these mattered. But so did timing and chance. Many other groups had equal claims to success, and many were lost by no fault of their own. To imagine dinosaurs as conquerors is misleading. They were the inheritors of emptied ecosystems, beneficiaries of luck written in lava flows and pulses of carbon dioxide. Their reign was possible only because others had first failed. We cannot know the full tally of what was lost. The fossil record is too incomplete, the gaps too wide. Entire clades may have come and gone without leaving a single skeleton for us to find. What we do know is that the Triassic was a time of evolutionary breadth unlike almost any other, and its extinctions remind us how thin the line is between endurance and oblivion. So when we think of the Triassic, perhaps it is best not to imagine it as a world waiting for dinosaurs, but as a crucible of possibility filled with lineages as valid as our own ancestors, whose only mistake was to exist at the wrong time. The acid trip ended not because it was destined to, but because geology drew the curtain. Volcanic eruptions lasting 600,000 years turned the atmosphere toxic and the oceans noxic. 76% of species fell silent. Only a fraction endured. And that is the closing note of the Triassic. A world remade twice within 50 million years, its survivors stumbling forward into a Jurassic landscape they did not plan to inherit. a strange collection of whiskered synapsids, small insect-feeding lizards, crocodiles in miniature, and the modest dinosaurs that would, by sheer accident, outlast them all. It is sobering to realise how much vanished there. All the oddities, all the flamboyance, all the improbable experiments, gone, leaving only stone records. The Triassic was not neat, not ordered, not a steady ladder of progress. It was messy, full of failures, brilliant in its chaos, and brutally cut short. It ended not with closure but with silence, a silence we can still feel in the gaps of the fossil record. And that is the reminder. Life does not build permanence, it builds what it can, when it can, and sometimes it loses even its greatest creations overnight. Dinosaurs like us are children of accidents, so the Triassic ends here, not as a beginning but as a vanished world, its wonders locked away in strata, its survivors stepping unknowingly into the next act. By the close of the Triassic, the planet felt both ancient and new. 50 million years had passed since the world's greatest extinction, yet the biosphere still carried scars of its own recovery. Forests had returned, rivers wound their way through floodplains, reefs flickered back into existence, and skies were filled with wings that had never flown before. Predators, prey, grazers, and giants had all risen in rapid succession, each staking claims in the fragile ecosystems that followed disaster. But the sense of stability was always an illusion. The Triassic world was not a calm plateau. It was a balancing act, with evolution improvising at a furious pace. Every lineage that thrived seemed to be shadowed by fragility, as though the planet itself had not yet decided which shapes of life would be allowed to endure. This precariousness is important to grasp before turning to the end. When we picture evolutionary history, we often trace a line directly to dinosaurs as if they were inevitable, as though the Triassic had been a waiting room for their arrival. Yet to the creatures living then, there was no sense of foreshadowing. An armadillosaur or a horned Shringosaurus was as real and successful in its moment as any later sauropod or tyrannosaur would be. The experiments of the Triassic mattered because they were experiments that worked, for a time. What would undo them was not their own inadequacy, but another planetary convulsion. And that convulsion came with lava. The central Atlantic magmatic province began to erupt at the seams of Pangaea, opening cracks that would eventually pull the continents apart. What to us is a clean line on a map, North America, Africa, Europe, South America drifting away, was, in the moment, a series of cataclysms. Gases poured into the air, carbon dioxide thickened the climate, and the oceans began to suffocate. This was not a single instant of disaster, but a drawn-out curtain call. 600,000 years of pulses, each one tightening the grip on ecosystems already stretched thin. It was here, in this drawn-out ending, that the Triassic finally gave way. What had been the most experimental, most chaotic period in Earth's history ended not with a flourish, but with attrition. Amphibians, armoured reptiles, flamboyant crest-bearers, even the largest of the marine ichthyosaurs, all were caught in the collapse. The survivors were a narrow cast of players, most of them small, adaptable, and in retrospect surprisingly ordinary. And that is where the final reflection begins. With a world that had been filled with strangeness, suddenly stripped down to the few lineages that would carry on. Thank you, fellow sapiens, for wandering this timeline with me, for drifting into deep time, for slowing down and remembering. If this helped you fall asleep, helped you study, or simply helped you step out of the noise for a while, thank you for being here. If you think more people should know this story, you know what to do. Like, subscribe, share it with the sapiens in your life, and tell me, are you listening before bed, while working, or somewhere in the world I can only imagine? And as always, stay curious, stay calm. I'll see you in the next story.